Hey, Hui, are you going to be sharing the video now, or should I just admit everyone and start the intro?
I'll share the video now.
Oh, okay, sounds good. Hi, good morning, everyone, or good afternoon or good evening, depending on where you are. Welcome. I hope you can hear me well. If not, just like indicate that you can hear me, but hopefully it's all good. Yes, good morning again, or like hello again, and welcome to the second Data Science Summer School organized by Hertie School Data Science Lab. And this year we are organized and funded by the generous support of the Hertie School, which we're very grateful for. And we just wanted to know that this year summer school, it's the second iteration of our summer school, will begin with introductory classes on programming and some mathematical foundations essential for the success of the data scientists. And this part is kind of part of the technical preparations for the Master of Data Science for Public Policy program that we have here in Hertie, but it is obviously open for everyone interested in learning all this like new things and new tools. So we're really welcome to see you and welcome you here today and on our following sessions as well. I'm extremely happy to see you all here today, both on Zoom, and we have a parallel stream session on YouTube. And I just want to like walk you through some of the technical and organizational details that you should keep in mind. So when you entered the Zoom call, your mics were muted and your cameras were off. So we kindly ask you to keep it that way, unless you have a question. But if you do have a question, preferably put it in the chat, and then we will try to address the question as soon as possible. However, if you do want to ask it out loud and unmute yourself and turn your video on to ask the question, please raise your hand first, and then we will kindly ask you to, we will invite you to actually ask a question whenever there's going to be a good time to do so. If you are joining us on YouTube today, you can leave your questions and comments in the live chat and in the comment section, and we will either address your questions ourselves or we will direct the question to our instructor. And I also want to remind everyone that the Zoom session is being recorded. So if you do unmute yourself and you turn your camera on, you're automatically agreeing to your voice and your image being recorded. And thank you very much in advance for following these rules. And I hope that's not too much of a trouble for you. And we all will going to have a good time today. Now, just beyond these technical details, I'm really, really happy to continue with our series of workshops today. And we have a third workshop in this series of events. And we're having the first workshop from the mathematical foundations today. And this is going to be calculus for data scientists. And let me introduce you our instructor today. It is Dr. Zuhair Desai. Zuhair is an assistant professor in the School of Global and Public Affairs at IE University in Madrid. And in his research, he studies electoral competition and political accountability. And his work spans both theoretical models of elections, voting, and policymaking, as well as empirical implications of these models in the developing democracies, such as India and Brazil. Zuhair, we're really, really happy to have you here today. Again, apologies everyone for some technical issues that we had at the beginning, but we're happy to go on with our workshop. And without further ado, Zuhair, the floor is yours and you can share your screen. And good luck, everyone. Thank you.
Can everybody hear me?
Yes, perfect. We can hear you.
So let me just share my screen. And apologies for the slight delay, as is always the case. There were some technical issues. Okay, can everybody see my screen?
Yes, perfect. We can see a screen.
So hi, welcome everybody. As Olga has introduced me very well, I don't really need to say much, but just to let you know, I don't really do machine learning in my work. I primarily work on game theoretic models and structural estimation of these models, but the tools that I use are the same tools that you would use in machine learning, because optimizing a utility function uses the same tools that you would use to optimize or minimize a loss function, for example. And the tools that you use for these techniques is called calculus. Please don't come on the board. Okay, I don't know who that person is, but you're on my board. Okay, so the tools that we use are the same tools that I use in my research. And the idea is that we work with functions and we try to see how that function varies and where we can find the maximum or the minimum of that function, broadly speaking, okay? So in order to do that, I'm gonna first start off really basic. I'm gonna go over functions. We're gonna work with differentiation or derivatives of functions in one dimension, first of all. We're gonna talk about applications, techniques of derivation, and this will probably take us about 1 hour, 45 minutes, at which point we will take a break. When we come back from the break, we will look at calculus of multiple variables, multivariate calculus. We will spend about an hour on multivariate calculus, primarily focusing on differentiation, so the gradient and directional derivatives, the chain rule in multivariable calculus. And then in the end, in the last hour, we will look at integration. And we will briefly cover some basic rules of integrals and what an integral actually represents, okay? So in order to start, I'm going to assume that you have some familiarity of sets and operations on sets. So for example, if you have a set A and B, and so I assume that you know what is the intersection of these sets, the union of these sets, etc. Okay, so I assume that you know all of that. And what we're going to start, first of all, is define functions more precisely, okay? So a function is essentially a rule or a mapping, sorry. So it's a rule or a mapping, and we denote it as F, which goes from a set A into another set B, okay? And what this function does is it assigns to every element of A an element of B. Okay, so that's pretty much the simple definition of a function. And what we're going to say is that for all little a, which is the element that belongs to, so this sign represents belongs to the set A, f of A belongs to B. So f of A is an element in B, okay? And in this case, what we will say is that A is the domain of F, and B is the codomain of F. Okay. All right. Any questions? I mean, it's pretty simple so far. Then certain other things that will be useful to understand what we do later on. The first thing is the image of a function. So if I take, for example, we started off with a set A, right? So let A prime be a subset of A. I'm assuming you know all of this, okay? And then F of A prime is called the image of A prime, okay? And essentially, it's all the elements of B such that there exists an A prime, and when I say A prime, I mean like little a prime, such that when I evaluate the function at that point, that function is equal to b, or little b. Okay, so that's the image of that function. A related concept is the inverse image. And we use this concept to define inverse functions essentially. So that's saying, take a subset of b. So basically the same idea as before, you let b prime be a subset of b, then the inverse image of b prime is essentially all the points in A such that the function value of that A is in B prime. Okay, so basically, if I give you a set B prime, the inverse image tells you what values of A give a B that belongs to that subset. Okay, so that's the essential idea of image and inverse image. Okay, and let's think about like an example of a function. So let's take a real valued function where the domain is in R, which is the set of all real numbers, and the codomain is also in R. Okay, and f of x is defined as x squared. Okay, so the domain and the codomain are the same, but if you look at the function value, you'll see that the range is not exactly R, right? Because x squared will always give us a positive number, right? So in this case, it's just like a note so that you remember that the codomain is not the same thing as a range. Okay, because for this function, the range is in fact the positive rates, right? While the domain was the set of all rates. Okay. Okay, so now let's look at some properties of functions. And by the way, if there are any questions, please speak up because it's really hard for me to monitor the Zoom. And if you have like a really pressing question or something that you did not understand, please just speak up, okay? Okay, so we're going to discuss some properties of functions. All right, the first thing is if I have a function that goes from A to B, okay, and the image of my whole set of the whole domain is in fact all of the codomain, okay, then we say that f is surjective or onto. Okay, basically every value of b is assigned to some value of a, right? And one example, for example, is x cubed, right? That is a surjective function. In fact, it is a bijective function. We're going to define that more carefully very soon. But that's the first property, that a surjective function is such that the image of the domain is in fact the codomain, right? And x squared would not really meet that criterion, right? Because all the negative values would not be mapped, or no point in the real line will give you a negative square, right? So that function, for example, is not surjective or onto. The second idea that we will work with is that if for all A and A prime that belong to our set A, and such that these 2 points are not the same, so A prime is not equal to A. If we have that f of A is not equal to f of A prime, okay, then we say that f is injective. Another way of saying it is that it's 1 to 1, right? So again, f of x is equal to x cubed is injective, right? Because each value of x will have a unique value of x cubed. On the other hand, x squared is not injective, right? Because minus x has the same squared as x, right? So x squared again is not injective, neither it is surjective, okay? And then the last idea is f is a bijective, or f is bijective if it is injective and surjective. Okay? And if it is true, if we have a function that is both injection and a surjection, then its inverse can be defined. Okay, basically it's a function which we will call f inverse. Okay, and this function goes from b to a. So basically f goes from a to b, but f inverse goes the other way around. And essentially the definition of this function is that for all a, f inverse of f of a is in fact a, and for all b, f of f inverse b is equal to b. Okay, are these properties clear? So if we find a function that is surjective and injective, then we get a bijective using which we can define the inverse. Any questions so far? Okay, so let's move on. And this whole idea of f inverse of f and f of f inverse, this is a more it's more broader than what I was talking about inverses, right? Because in fact, what it is a composition of a function. So let's discuss compositions more precisely, okay? And essentially the idea is that if the domain and codomain of two functions, let me write this better, sorry. Coincide of two functions. So sorry, that must be clear. We have two functions and their codomains and domains coincide, then we can apply them to construct a new function. Okay, and I'm going to define that more precisely. So let's call this definition. So let f be a function that goes from a to b. Okay, and let g be a function that goes from b to c. Okay, so then what we say is that the composition of f with g, and by the way, this is just means width. I will be using this a lot, so please remember this. When I write a w and a slash, I mean width. It just saves time. So the composition of f with g is basically the function. So it's a new function, and we're going to write it in this way. So we're going to say g, and I'm going to draw a circle f. So basically it's g of f of x, okay? And this function basically goes from a to c, okay? So basically it goes from a to b, and then it goes from b to c, right? And And we're going to write that G F at some point A is basically G of F of A. Okay. And this is going to be very important when we discuss the chain rule, for example. So let's start now. All right. So let's give a few examples unless there are any questions. We will talk a little bit about how this applies to data science, but it's primarily a review of calculus that will be used in data science or in machine learning. Okay. All right. So let's go to the new page. We're going to discuss a few examples. So f of x is equal to 2x plus 3. Okay. And they're both real value functions. Okay. And g of x is equal to x squared. Okay. So what does this mean about g of f of x? Okay. And it's quite simple, really. So g of x is x squared. So g of f of x has to be f of x squared, using some notation. Okay. And then we know what f of x is. F of x is 2x plus 3. So that is just 2x plus 3 whole squared, right? So this is how you construct a composition. I started with two simple functions and I came up with a slightly more complex function. All right. And it's a very powerful technique and you can use it for, a lot of different tools. So using the same idea, let's do the composition f g of x to show you that these are not the same. Okay. So essentially composition is not a commutative property. All right. So f of x is 2x plus 3. So using some notation, f of g of x is 2g of x plus 3. And then I know what g of x is, and that's just 2x squared. 2x squared plus 3. So as you can see, g of f of x is not equal to f of g of x in the sense that this is not a commutative operation, right? It is associative in the sense that if I have three functions, f, g, and h, then it is true that if I take the composition of f of g, f and g, and I take the composition with respect to h, it's in fact the same thing as taking the composition of f with the composition of g and h, okay? So it is associated, but it is not commutative as this example proves. Okay. Any questions so far? Okay. So now let's start with calculus. All right. And we're going to be working with primarily functions in one dimension. All right. And calculus, broadly speaking, and very broadly speaking, it's not a very precise definition what I'm just about to give you, is just a mathematical study of continuous or smooth changes in a function. All right. And in particular for this class, because in machine learning, most of the functions are real value, we're going to be considering real value functions only. And for this first part of today's course, we will be considering functions of only one variable. Okay, so we will consider real valued functions of the following form. So it takes a set A into R, and we will assume all throughout that this A is in fact some subset or could be even the real line. All right, so this is the basic idea. We're going to look at functions of this form and we'll try to see whether we can develop tools to assess how this function changes at any point and around that point, right? We will basically try to be answering questions. What is the rate of change of this function at a particular point? What is the sum of values of that function around a particular point, etc. Whether that function is continuous at a particular point or not, right? So we will be developing tools to answer questions such as this. And this will be applied in your machine learning process later on in your program, all right? So some interesting and important functions are as follows. Before we actually start analyzing them, let's talk about certain special cases of functions, all right? The first is what I call affine functions. And essentially, it's any function f of x of the following form, ax plus b, where a and b are both real numbers. And x obviously is a real number. All right? It's like a linear function with an intercept, right? The second is polynomials. These are very important in machine learning, definitely. Okay, and essentially, a polynomial of degree k exists if there exists coefficients, which we will call a1, a2, all the way to ak, and there's no restrictions in them as long except for the fact that they're real numbers, right? One restriction is that ak has to be non-zero, right? Otherwise, it would not be a polynomial of degree k, essentially. All right. I'm just going to write this here, such that for all x in R, f of x is essentially, so I think a0 was important, a0 plus a1 times x plus a2 times x squared, all the way to ak times x raised to k. Okay, and I can write this more succinctly using a summation. So I basically goes from 0 to k, ai times x raised to I. Okay, so very succinct definition of what a polynomial is. We'll be working with polynomials a lot when we discuss techniques of differentiation because they're very easy to work with. They're nice, smooth functions. Okay, we'll define smoothness as well. Another important class of function are exponential functions. You probably have heard of them. And we're not going to be going into the definitions of how to derive these functions, but we're just going to briefly talk about what they are and some properties. So essentially, it's just f of x is equal to e, where e is Euler's number, e raised to x, also often written as exp of x. So I will be using this notation later on, so just so that you know what it is. And some important properties are as follows. For any x, the exponential of x is always positive. Okay. Another property is that if I take two numbers, x and y, then the exponent of x times the exponential of y is simply exponential of their sum. And you probably know all of this already, but just to give you a brief background for those of us who don't or are not familiar with these functions, this is pretty much it, and these are some of the properties it satisfies. Another important function is the natural logarithm. And again, I will be using this in the examples that we will be working through. So this is a natural logarithm, usually called log, usually defined as ln, to say that it's natural log and not with some other base. Okay, and essentially this is a function that basically only the domain is the set of all positive and strictly positive real numbers. So that's why I write two pluses here, because it does not include 0. Okay, and maps onto R, okay, where f of x is basically or log x, sometimes also ln x. If I write log, I mean the natural base, so ln. All right, and some important properties of log combining with the properties of exponentials are as follows. So log of the exponential at x is in fact just x. And this is an important identity that we might use when we do integration later on, because integration is kind of weird. Sometimes you need to use tricks like these. So it's important to just give you a brief overview of what these tricks are. And similarly, the exponential of log of x is also x. So basically, they are like inverses in a way. Okay. And this is only true, obviously, if x is strictly positive. And there are some other properties like the log of fraction is just the difference of the logs. And similarly, the product and for example, you would use this in maximum likelihood methods. Taking a likelihood function and converting it into a log likelihood function, which is not a product, but a sum. So it's, concavity is easier to find. And then there are some other functions, which are trigonometric functions and inverse trigonometric functions, which I'm not going to talk about in detail because it's not going to be used a lot more in what I'm going to go through today. But it's basically sine functions, cosine functions, wave functions, for example, and their inverses, so arc cosine, arc sine, etc. And I'm not going to be going over them in any detail for now, at least. All right. Are there any questions? Or there were some questions, I guess Olga took care of them. R++ means, yes, the set of all strictly positive real numbers. So 0 is not included. Right? If I say R++, if I say R+, then I include 0. It's basically weakly positive. Okay. All right. So now we know what functions are. We talked about some properties. We talked about some basic functions. The next thing we're going to discuss is sequences. And this is very important because calculus is the study of smooth changes, right? So we need to be able to define what smooth is. And in order to do that, we use sequences. So the next unit is sequences. Okay? It's basically a special type of a real valued function, right? And what it does is it allows us to speak about closeness. What happens if I look at points close enough to a particular point, right? And this is the basis on which we will define continuity from. All right. So essentially, a sequence is a special kind of function. It basically is a discrete function, obviously, and it's a list of numbers, right? X1, X2, X3, and it goes on forever. It's an infinite sequence, right? And all these numbers are real numbers. So essentially, you can think of sequence as a function that maps the natural numbers. When I say natural numbers, I mean numbers like 1, 2, 3, and so on, all the way to infinity. So it maps a set of natural numbers, which is a subset of the real numbers, to the real numbers. All right. So that's what a function of a sequence is. All right. Such that f of xn, or sorry, f of n is equal to xn. Right. So if I have a sequence, it's essentially a function. And it's mapping each natural number into a real number. All right. So some examples. So 213 is not a sequence, right? Because it just ends. It's just a list. It's not a sequence. This is a sequence though. So 2, 3 by 2, 4 by 3, 5 by 4, and so on and so forth. This is a sequence. All right. And in fact, it can be written as a function. And so essentially, we will write this as n plus 1 over n, right? And then in order to indicate that this is a list, it's not a particular number n, I'm just going to say that n is a natural number. So this is not one particular number, it's a list, it's an infinite list of sorts, okay? Another sequence is 4 minus 2, and then, for example, this just stays at 1 forever. It's still a sequence, even though it's reached some sort of bound and hasn't changed from there, right? It's still a sequence. And a last sequence, a very important and fun sequence, is the one that alternates between -1 and 1 forever, okay? And this also can be written as a function. So, for example, this would be minus 1 raised to n. And again, in order to indicate that this is an infinite list, I'm going to say that n is a natural number. All right. So this is essentially the idea of a sequence. And for example, we can talk about the bounds of a sequence, right? So if I look at this sequence, n plus 1 over n, right? If I look at this sequence, and let's just draw it out just to see it more clearly, right? So it starts at 2, right? Because n is a natural number, so the smallest one is 1. So 1 plus 1 is 2 over 1 is 2. Okay. All right. And then the next one is 3 over 2, which is essentially 1.5. Right? So that's 3 over 2. Okay. The next one is 4 over 3, which is essentially 1.33. So it's probably somewhere here. Right. So that's 4 over 3. And then the next one is 5/4, which is 1.25. And so on and so forth. So you can see that it's decreasing, right? It's a monotonic sequence. It's monotonically decreasing. And then the second thing you can see is that it is bounded above by 2, right? Because for whatever it starts at 2, when n is equal to 1, the first value is 2, and then it's monotonically decreasing from that point onwards, right? So the upper bound is clearly 2. So this sequence is bounded above by 2. And in fact, it's bounded above by 3. It's bounded by any number that is greater than 2. But this is the least upper bound, right? This is the smallest upper bound. So this is bounded above by 2. And then we see that as we increase n, we keep on moving to the left, to the left, to the left, slowly, 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 slowly. But we'll never really reach 1, right? It'll always be slightly greater than 1. But in the limit, if I go far enough, it'll be essentially very, very close to 1, right? Because if as n goes to infinity, this ratio converges to 1, right? So then it's bounded below by 1, sorry. Right, and essentially the idea is because this quantity is converging, and we're going to discuss this in more detail, but it's converging to 1. All right, and we're going to talk about how we can show something like this. Are there any questions so far?
Zuhair, there is a question in the chat about sequence. Like, can you maybe elaborate a bit more about that? The person did not understand the idea.
Basically like a list of numbers, right? And it's an infinite sequence. So it just keeps on going forever. All right. And this is a sequence because, for example, n plus 1 over n, if I take all the natural numbers, so from 1 to infinity, if n is equal to 1, I get 2. If n is equal to 2, I get 3 over 2. N is equal to 3, I get 4 over 3. And for any value of n, I'll get a number here, right? So this is a sequence of numbers. It has like a particular pattern, which I can actually write down as a nice function. And it's a collection of points, right? It's a list of points. No, because n is a natural number. So that's why 0 is not really included. So it's x1 all the way to infinity, right? This is clear, Hussein? Okay, no worries. Okay. So when we talk about sequences, we want to talk about the limits of sequences. So we need a form or a measure of distance between points, right? Like how close a point is to another point. Are all pattern sequences. There are some sequences that don't have a good pattern. So for example, this one, right? I mean, eventually it hits some sort of pattern, but in the beginning it didn't. But all patterns of this form, if you can write it like this as a function of natural numbers, then it's a sequence, yeah. Okay, so what we need is a function to define distances between points. And obviously we know what function to use in one dimension. I'm going to write it down here because then in multiple dimensions it gets a little more complicated or weird. So let's just start now, right? So that function is clearly the absolute value function.
Zuhair, sorry for interrupting. There is a couple more questions about sequences. So is 0 not included in sequence, correct?
Yeah, I already answered that. So that's because, I mean, essentially, it's not really 0. I'm just saying that it's a function that goes from the natural numbers. So when I define sequences, there's always a first value of the sequence, second value of the sequence, so on and so forth. Is that all? I think that's all, right?
Are all patterns sequences?
Yeah, I already answered that, right? I'm saying that not all sequences are real patterns, like this one. I mean, eventually it becomes a pattern, but not in the beginning. But if you have like a function that you can write in this form, then it clearly is a sequence, as long as it's a function of natural numbers. Okay?
Thank you.
Yeah. All right, so let's move to the absolute value function, because we want to define what sort of continuity is, what limits are, and for that we need how close functions are to each other, right? And essentially a limit of a sequence. So for example, if I take this sequence here, it keeps on going down, right? It keeps on decreasing down. It never actually hits one, but it becomes arbitrarily close to one, right? So we need a function of closeness to see whether any sequence has any regularity as n grows very large, okay? And we need a notion of distance, and obviously in one dimension, that notion of distance is the absolute value function, and I'm going to define that now. So basically the absolute value of x is, and when I do this, I say it's just basically a case-wise function or piecewise function. So the first case is it's equal to x if x is positive, and it is minus x if x is negative. Okay, so basically any value you give it, it's going to give you a positive number. I mean, if I draw it out, it's going to be two lines, right? Something like this. So this is absolute value of x. Okay. So the distance between 2 points, so using this function, and I'm not going to, well, let me just talk about distance first. So distance between 2 points. Okay, so let x and y be real numbers, right? So the distance between x and y is the absolute value of their difference. A lot of you probably already know this, but let's just build all of this from the ground, okay? All right. And then some properties are obviously as follows. Obviously, x, the absolute value of x minus y is always equal to positive, and it's only equal to 0, right? If and only if x is in fact equal to y. Okay? And then the absolute value of x minus y is equal to the absolute value of y minus x. And then this is what is called the triangle inequality. Basically, the distance between 2 points directly is always less than if you took a detour, right? So if you took a detour to z, and then you went from z to y. So directly going from x to y is always going to give you a smaller distance than if you took a detour, essentially. This is called the triangle inequality. Okay. All right, so now that we know what sequences are, we know what's the distance between 2 points. Now we can define convergence of sequences, right? So for example, let me just go back to the sequence here, right? This sequence, -1, 1, -1, 1, right? It goes very close to 1, but then it immediately goes away, right? This sequence, it starts at 4, goes all the way to -2, and goes to 1, then it stays there. So in a sense, it's sort of converging to 1, right? It's going to remain 1 forever. This sequence starts at 2 and monotonically decreases. It always decreases, right? It never hits 1, right? But as I said here, as I showed you in the picture, it gets very, very close to 1. So if n is really, really large, the distance between that sequence value and 1 is going to be arbitrarily very small, right? So that's the idea of convergence. This sequence is converging to 1, even though it never actually hits 1. All right. So let me define that more precisely. So a sequence or sequence convergence. Okay, so we have a sequence xn, and as I said, it's not a number, it's a sequence, it's a list. We say that it converges to some number x if it eventually gets, and more importantly, stays arbitrarily close to x. Okay, so that's the precise and formal definition of what it is to have a convergent sequence. And just to go back to the examples that I gave you here, right? Here in this sequence here, this one, this sequence gets exactly at 1 and exactly at -1, depending on what n is, right? But it never actually stays there, which is why this sequence is not convergent. This sequence gets to 1 and then it stays there forever. So it is converging to 1. And this last function, or this sequence here, as I showed in the diagram in the next slide, it gets arbitrarily close to 1, never actually hits 1, but it gets extremely, extremely close to 1. So this is also a convergent sequence and it's converging to 1. No, so basically the idea is a sequence, right? So it's a list. So I need to have a first number of the list, a second number of the list. So that's why we define it as a function of natural numbers. And a sequence is basically like an infinite list. The number of elements in that list is infinite. Okay? All right, let's move on. Okay, so we talk about sequence convergence, and basically a mathematical definition is that, so I'm going to write this down with like a preface that it's a mathematical definition. We say that xn converges to x if, and I know maybe this is too much, but it's just a mathematical definition of what I wrote here. So I'm saying if all positive real numbers epsilon, if I can find some n, which is a natural number, such that the distance between xn and x, okay, is less than epsilon for all little n greater than or equal to capital N. Okay, and what we're going to say is that xn is converging to x, or that the limit as n goes to infinity of xn is x. Okay, and just to give you, look at the picture that we drew here, right? So suppose I say epsilon is equal to 0.75. Okay. Okay. Well, what if I chose n is equal to 2, right? Because this is 1.5, right? This is 1.5, so x2 is equal to 1.5, which means the distance between x2 and 1 is 0.5, which is less than 0.75. And then for all, the distance between any sequence number that is greater than x2, right, or that comes after x2 and 1 is always going to be less than 0.75, right? And if, for example, I say epsilon is equal to 0.4, then if I choose n is equal to 3, right, then this thing is 1.33. So the distance between this point and 1 is 0.33, right? Essentially, any sequence value that comes after 4/3, the distance is going to be smaller than 0.33, which means that, for epsilon is equal to 0.4, I can also find an n such that the distance between all the sequence points that come after xn, when I say xn, I mean x3 in this case, is always going to be less than 0.4. Okay? I can't zoom out, sorry. Because it's like a different slide. Okay? So that's the idea of sequence convergence. All right. So now we're finally going to do calculus. All right. So the next R is calculus, and in particular derivatives. All right. Let's go. So essentially, if I have a function, okay, if I have some function, I will put the slides up later on, and we don't have enough time. So I'm sorry, I'm not going to go back to the sequence convergence slide, but I will post all of these slides up. All right. So suppose we have some point x naught, right? And then this is the function value of x at x naught, right? So the questions that we're going to ask is f smooth at x naught, right? What is the rate of change of f at x naught, right? How fast does it increase at that particular point? What is the sum of values around x naught, right? That sort of questions, we need calculus to answer these questions, all right? And in particular, what we first start from is limits, all right? And first we look at one-sided limits, okay? So for example, if I take a sequence of points, right, that starts somewhere to the right of x naught, okay? So for example, suppose it starts here, all right? And just suppose for simplicity's sake, it's a decreasing sequence. All right, so basically it keeps on decreasing, and keeps on decreasing. And basically, suppose this sequence, whatever sequence this is, I haven't actually defined it, but doesn't really matter. It just goes slowly all the way to x naught. Okay? And what we do is we look at how f of x behaves as this function goes close to x naught, right? So at this point, I haven't actually drawn it. But for example, f of x goes from here to here to here to here. So we're basically tracing f as the sequence goes to x naught. We're tracing the values of the function, right? And then it converges to some particular point, right? Because this is a convergent sequence. And if x is continuous, it's going to converge somewhere. Okay, so we say that it's a left-hand limit. Okay, so, or sorry, this is the right-hand limit. So I'm going to say the limit as x goes down to x naught from the right of f of x is some number r, right? This is the right-hand limit. And similarly, left-hand limit is the other thing, in the sense that you start from a sequence to the left of x naught, all right, that converges to x naught, and then you look at how the function behaves as that sequence converges, right? And you see what sort of thing it converges to. So from the left, it goes up to x naught. That's why I wrote the up arrow here. Of x is equal to some number L, it will be some number L, or maybe it doesn't exist, but let's suppose it does exist and it's some number L. And that is the left-hand limit. Okay. So we've used the ideas of sequences, convergence, and limits in the idea of functions. Okay. And then the idea is that the limit of that function exists if the left-hand limit is equal to the right-hand limit then that limit of that function at that point exists. So limit of f as x, any sequence or any point approaches it exists, and it is denoted by so now I don't have an up or down arrow. It doesn't matter what side I come from it. Okay, it doesn't matter what side I come from. Whatever direction I approach x naught from, this limit exists, and it is given by this number. Okay, and sometimes limits don't exist. Okay, so let's look at this function here. So suppose f of x is equal to 1 over x. All right, let me just draw it out for you here. Okay, so as x goes to 0, 1 over x is becoming arbitrarily large, right? But we don't really know what 1 over 0 is. That's undefined. Okay, and similarly, when x is negative, it's becoming even smaller, and minus 1 over 0 or whatever it is doesn't exist, right? So what we say or what we write is that the limit as x approaches 0 from the left is negative infinity. It doesn't exist. We're going to write negative infinity because it's going to be arbitrarily small, right? And similarly, as I approach x 0 from the right, it's positive infinity. But again, the idea is that it doesn't really exist because it's blowing up, right? So the limit of this function does not exist at 0 for two reasons. First, because neither of these limits exist, the left or the right hand limit, they don't exist, and they're not even the same, right? Like minus infinity and infinity are clearly not the same. Okay, this is actually what is called an essential discontinuity. All right, are there any questions? Okay. Seems like we are good. Okay. So let's talk about continuity, because now we have all the tools to define what continuous function is. Okay, because the limit or the idea of a limit allows us to speak what happens to f in a neighborhood, right? Or in an area that is close to some point. Okay, and the definition or the precise mathematical definition of a continuous function is essentially that f is continuous at some point x naught, which belongs to some interval a and b, if the limit at that function or at that point is in fact equal to what that function gave to that point. Okay, the value that that function gave to that point. And so this is continuity at a point, and f is in general continuous if it is continuous at every point. I'm going to write cont dot just as a short form. Okay. So that's the definition of continuity. Are there any questions so far? Regression discontinuity? No, this is not that class. It's just calculus. All right, that's econometrics, that's causal inference. It's not really what we study here, at least. But hopefully in the course of your program, at some point you will, okay? All right, so now we know what a continuous function is, all right? So the first question that I had was, if I have a function like this, how do I know if it is continuous at a particular point? Well, it's quite easy. If the left-hand side and the right-hand side limits exist and they're the same, then that function has a limit at that point, right? And if in fact f of x0 is in fact equal to the limit, right? Then that function is continuous at that particular point. All right, and in general, it's continuous if it is continuous at all points. So the next thing that we want to talk about is the rate of change, right? So the next question that we will try to answer is how fast does f increase or decrease at some point x0, right? That's the question we have. Okay. So just to give you an example of why or what we're going to do is, suppose we have some sort of function, right? Suppose it's given like this. Okay. So now suppose this is my point x0, right? That I want to find out how quickly does this function increase or decrease at this point. Okay. Now, suppose I look at this point here, x0 plus some number h0, right? So I draw the points here, okay? All right, and I draw like a secant line between these 2 points, okay? So what is the slope? And this is, geometry. So the slope of this line is essentially f of x plus h0, or x0 plus h0 minus f of x0 divided by h0, right? Now suppose I take an h that is smaller than h0, right? But still positive. So suppose I look at this point here, x0 plus h of 1. Okay, and then I look at the secant line between these 2 points. Okay, the slope of this line, on the other hand, similar form, but not the same. It's f x0 plus h1 minus f of x0 divided by h1, right? And if I continue this process, right, if I continue making h smaller, eventually I'm going to get a tangent line. Right? That is to say, if I move x slightly to the right of x0, this would be the slope of that line. And that is in fact how quickly that function is increasing at that particular point. Okay? Does this make sense to everybody? So basically, a derivative is essentially a slope, and in fact, it is a tangent line, right? And in this example, we took a sequence from the right, right? We took a sequence from the right, and we slowly converged to the point that we were interested in. And we saw that the slopes converge to something, right? Because h is a sequence, right? h0, h1, it's a sequence, it converges to something, right? And in fact, for example, the right-hand side derivative, which is what we looked at, so I'm going to write that here. I'm going to say right-hand side derivative. It's essentially defined, and it's basically a function, and I'm going to write f prime or f dash, and I'm going to write a plus here because I'm denoting that I'm coming to it from the right-hand side. At a particular point is essentially the limit of this function here. So this is the rate of change at x0 if I approach it from the right. Okay, and similarly, the right hand or the left hand side derivative I'm going to denote this f prime minus x naught, and essentially it's the left-hand side limit, okay, of this slope, essentially. Okay, and if both of these derivatives exist at this function, at this point x naught, right, and if they are the same, then we say that f, so I'm going to say if both exist and are the same, okay, then we say that f is differentiable. So first we talked about continuity, now we're talking about differentiability. So if both these limits exist and are the same, then f is differentiable at x naught. Okay? And the derivative of f, which is the rate of change of f at x naught, is given by this limit. Okay, so we started with a general function, and using sequences and continuity, we've established what the derivative is, whether it exists or not, and what does it look like? Essentially a limit. Okay, so this is important, right? This defines the derivative at a particular point. All right. And f is differentiable in general if it is differentiable at all points in its domain. All right. Now, this is the Newtonian notation, which is f prime. Some other notations that you may have seen and that will be useful because I will be using them is the Leibniz notation. So basically, that's df dx, which is saying what are the changes in f as x changes arbitrarily. That's why it's a d instead of a delta, right? Because the delta is like the x1 minus x naught, for example. Okay, so this is another notation that we will be using, and I'm just introducing it because later on I don't want you to be confused. So when I write df dx, I mean what is the derivative of f at with respect to x. Okay, are there any questions before I move on? So now we're going to talk about the techniques of differentiation. So we're going to spend the next 40-50 minutes on some simple techniques of differentiation, and you'll see that differentiation is amazing, but it's also super simple. And at the end of this course, we will talk about integration, and that is a different beast and slightly more subtle and more complex. Yeah, we have introduced smoothness. Essentially, it's differentiability, right? Because if I can find the derivative at any point, then it is smooth, right? Does it make sense? Okay, cool. All right, so let's talk about the techniques of differentiation. Okay, so we're going to do a lot of stuff now, right? We're going to do a lot of weird things. We're going to look at a lot of weird functions. And there's going to be a lot of algebra involved, which I will do quite fast. But if you can have a look at this video later and go through it line by line yourself, okay? But I want you to remember, we're talking about differentiations. Essentially, these are techniques of finding some slope, right? We looked at it here. Basically, a derivative is the slope of this tangent line. So everything that we're doing is just finding slopes. So just keep that in mind as we go along, because we're going to get into algebra. We're going to do a lot of weird stuff. Sometimes it's easy to forget what we're actually doing it for. All right, but we're going to do it to basically find the slope of a function. So let's start with a simple function. Let's suppose you have a function f of x, which is just x squared. Okay. All right. So now we want to find the derivative or the slope of the tangent line to that function at any given point x, right? So we look at the definition that we've already developed, all right? So we're going to say d of dx, which is to say that we are differentiating with respect to x, this function f of x. Okay. All right. So that thing, if you remember our limit definition, it's basically the limit as h goes to 0 of x plus h squared minus x squared divided by h. Yeah, we are going to go through the derivative rules right now. Okay. So we start from this thing. We know that this is the definition of a derivative, right? Now we have this limit as h goes to 0. If h goes to 0, then this denominator goes to 0, which means that clearly this limit would not be defined, right? That's an issue. So we need to get this h out. We need to get this h out, and given our function, it's actually really nice and simple to do that. All right, so let's just expand this, all right? So this is the limit as h goes to 0, okay? X squared plus 2xh plus h squared, all right, minus x squared divided by h. And then we do a little more algebra. So it's the same thing as limit h goes to 0. So the first thing is that this x squared cancels, right? So then all we have is 2xh plus h squared divided by h. And now it's nice because now we can take the h out, right? Because there's an h here, there are h times h here. And we can simplify this. I'm just going to write that here. So essentially, this is the same thing as the limit as h goes to 0, h 2x plus h divided by h, right? And then this h cancels out. Okay. And then now we know, right, as h goes to 0, this thing goes to 0, but 2x remains. So in fact, the answer is that the derivative of f of x, where f of x is x squared, is in fact 2x. And a lot of you probably already know this because this is the power rule of differentiation. So this is the first rule, derivative rules, that is the easiest to understand and it's very powerful. Essentially, the derivative of x raised to any power n, okay, is n times x raised to n minus 1. All right, and this is very important. This is our first rule. Yes, it is the power rule. All right, and then let's do some simple examples using this. Okay, so for example, d of dx of x raised to 5, it's very simple. It looks hard. And for example, if you were actually using the definition of a derivative, it would be kind of annoying, right? So you have x plus h raised to 5. It's hard to expand that, right? But with this rule, it's quite simple. So it's just 5 times x raised to 5 minus 1, which is 4. Okay? All right, now let's do something that is slightly more weird. What would be the derivative of x raised to minus 3? Okay? The rule still applies because I do not give any restrictions on n, right? It's a real number, which means that the derivative of this thing is just minus 3 times x raised to minus 3 minus 1, which is minus 4. Okay? So now you know how to get the derivatives of most, powers, right? Like x raised to any power. What if somebody gave you this function, 1 over x? Okay? Looks weird because it's not in this form, x raised to n, but we know this. This is the same thing as x raised to minus 1, right? And now we can apply this rule. It's just minus 1 times x raised to minus 2, which is in fact just x raised to minus Okay. Are there any questions so far? All right. So then the next rule is that the derivative of any function multiplied with a constant is just that constant times the derivative of that function. This is not the product rule because this is a constant. Okay? C is a constant. C does not depend on X. All right, so that's the next rule that we'll be discussing. And this allows us to do even more fun stuff. So for example, if I gave you a function 5x raised to 4, and I ask you the derivative of that function. Well, now I know that I can just take the 5 out, doesn't matter. So this is the same thing as we did before. So that's just 5 times 4 times x raised to 3, which is to say 20 x cubed. Okay, and even do stuff like minus x raised to 7, for example. It's the same thing, right? Because this is minus 1, we just don't write the 1. Okay, so we can take the minus out, and then we can just take the derivative of x raised to 7, and we know that, so that's minus 7x raised to 6. Okay? Are there any questions? Okay. Next rule essentially says that if you have a sum of two functions, right? So for example, if you have in general form, if you have d dx of f of x, and I'm going to say plus or minus because it doesn't matter what the rule is called. I don't really know the name of the rules. This one is just like the constant, you're just taking the constant out. The 4, let me see. Oh, from this, right? Because the derivative of x raised to n is n times x raised to n minus 1. So this 4 comes down here. Okay, and then that 4 becomes 3 because 4 minus 1 is 3. Is that good? Okay, so the next rule is basically saying that if you have a sum of two functions, and when I say sum, I also mean like difference, because as we know by this rule here, the constant can just be taken out. It's basically, I can distribute this d over d of x inside this sum. Okay, so that's d of dx of f of x plus or minus d over dx of g of x. Okay. All right. And now we can do even, in fact, now we can do all polynomials, right? All polynomials and even more so. Okay. So for example, if I give you a function, which is, and I ask you to find the derivative of that function, which is 3x raised to 9 minus x raised to minus 3. Okay. Now, according to this rule, I can distribute it inside. So that's the same thing as d dx dx raised to 9 minus d dx of x raised to minus 3. Okay, and now I apply the rule for constants. I take the constant out, so that's just 3 times d of dx x raised to 9, and then this I already had everything here, so that's just multiplied by minus 3 x raised to minus 4. Okay, and then this thing is 3 times 9, x raised to 8. And then now minus times minus becomes plus. That's plus 3 raised to x minus 4. And then the last simplification is 27 x raised to 8 plus 3 x raised to minus 4. Okay? All good? Okay. All right. And then let's do one last one, which is perhaps slightly more confusing, but we use the same logic. All right, so let's take this function 4 minus 3 square root of x. Okay, so now all we've done is the power rule, right? So we've only looked at powers, and this is square roots looks weird, right? But in fact, you can write square roots in this way. d of dx, 4 minus 3 x raised to half. That's the same thing as a square root. Okay, and now we can apply our rule. So the derivative of 4 is what? It's 0, right? Because essentially it's 4 x raised to 0, which is equal to 4, because x raised to 0 is equal to 1. So essentially you take 0 out and the derivative of 4 becomes 0, right? So the first part, dx of 4, this is in fact 0. Okay. Minus 3 times the derivative of x raised to half. As I said, this thing is 0 minus 3, and now is the weird part, right? It's a half, but it's the same concept. So I just take the half out, okay, and then I do x raised to half minus 1, which is to say x raised to minus half. Okay, and then we can rewrite this in more beautifully. It's just basically minus 3 divided by, I told you that x raised to half is the square root of x, which means that the x raised to minus half is 1 over the square root of x. So that's it. Okay. So we have weird functions, but using the power rule and these other rules, the constants and sums of functions, we can easily find the derivatives of most functions out there. Okay. And now we're going to talk about product and quotient rules. So try to build up our knowledge of how to differentiate slightly more complex functions. Okay. So I'm going to write product and quotient rules.
Я наушники надела.
Получается, они подключились сюда?
Нет, они подключились к телефону. Они, почему оно так не работает? Мы все время...
Someone is unmuted. Could you please?
Автоматически.
Okay, so suppose we have two functions, f of x is equal to, let's say, x, okay? And you have g of x is equal to x raised to 5. All right, and then the question is, what is the derivative of product of these functions? Okay. Okay, so let's do it two ways, okay? Let's do it by brute force, by actually just multiplying these two together, because they're quite easy. And then let's look at the rule that we're going to develop, all right? So this thing, d of dx of fx times g of x is essentially x raised to 6, right? So that's 6 x raised to 5, all right? And then the first question that I have is it true that this thing is the same as this thing? Because with sums, we could do this, right? So the question is, this is the same. Well, if we do it separately, we see that it's not, right? Because the d of dx of x multiplied by d of dx of x raised to 5 is in fact, so this is 1 multiplied by 5x raised to 4. So clearly, the derivative of a product is not the product of the derivatives. All right. This is not the same thing, but I'm going to give you the rule for general products. So that rule is simply saying that the d of dx of f of x times g of x is in fact equal to f prime x multiplied by g of x plus f of x multiplied by g prime of x, where this is just the derivative of f with respect to x, and this is the derivative of g with respect to x. Okay? And let's use this rule. So this is called the product rule. It's a very important rule in calculus, and also for integration later on, as you will see. So let's go back to our example, d of dx. We had x times x raised to 5. And we already know what the derivative is because this is a simple function. But let's just use the product rule. Okay, so the derivative of f, which is x, is just 1. So that's 1 multiplied by x raised to 5. Okay, plus f of x is x multiplied by the derivative of g, which is x raised to 5, and is therefore 5 x raised to 4. Okay, and then that becomes x raised to 5 plus 5 x raised to 5, which is 6 x raised to 5. Okay, and if we go back a slide, this is in fact what we got when we did the brute force method, when we actually multiplied them out together, right? So this product rule works. I mean, obviously it works. People a lot smarter than all of us proved it hundreds of years ago. But this is just a small example to show you that it works. And it was an easy function, okay? But now let's look at a more complex function. So suppose f of x is equal to x squared plus 1, 3x4 plus 2x cubed. Okay. Now, of course, you could distribute all of them, right? The whole expression, expand it, and then use the power rule. But the product rule is simpler, right? Because you don't need to do all that complex algebra. You still need to do some algebra, obviously. So let's see, d of dx of f of x. Okay, so now we have a product of two functions, because this is a function, this is a function. These are two separate functions, right? So what we're going to do is we're going to apply the product rule. So we're going to say first we differentiate x squared plus 1, and we just multiply 3x raised to 4 plus 2x cubed, okay? And then we're going to add, because that's what the product rule is, x squared plus 1 and then we're going to differentiate the second function, which was okay. And this is an easy function to differentiate, right? So that's just 2x, the derivative of 1, remember, the derivative of a constant is 0. Okay, so that's just 2x multiplied by 3x raised to 4 plus 2x cubed. Okay, and then this one is x squared plus 1 multiplied by the derivative of the second thing. And again, now it's easy, it's just a simple polynomial. So that's just 12 x cubed plus 6x squared. Okay, and then if you wanted, you could make this look nicer. You don't have to, obviously. And I'm not going to, show you all the steps I did, but essentially this is what it would look like if I did all the algebra and just expanded everything. It would look like that. You can do that yourself if you don't believe me. Okay. Let's do a slightly more complex function. And then we'll move to the quotient rule. So suppose f of x is equal to 1 plus x raised to 4 times the square root of x. Okay, and I can rewrite this, right? Because we know what the square root of x is. 1 plus x raised to 4 times x raised to half. Okay, and then we use our product rule. D dx f of x is nothing but d by dx 1 plus x raised to 4 multiplied by x raised to half plus 1 plus x raised to 4 multiplied by d over dx of x raised to half. And then just continue solving. I mean, this is easy. It's 4x cubed multiplied by x raised to half plus 1 plus x raised to 4 multiplied by 1/2 times x raised to minus half. I'm going a little fast, but these are very simple application of the rules that we've just done, right? Because these are all polynomials of sorts, and it is really easy to get the derivative of polynomials. Another reason why actually they're liked a lot in machine learning, because they are nicely behaved functions, okay? And then just doing the algebra, I'm not going to show you all the steps, but essentially it becomes 9 by 2 x raised to 7 by 2 plus 1 divided by 2 square root of x. Okay. And again, you can do the algebra on your own if you don't feel comfortable, or if you don't really understand how we got from the second equation to the third equation. So it's just algebra, and it's good practice to just do that at home if you are not convinced by this. Okay. So that was the product rule. That was how to differentiate functions that are products of other functions. The next thing is, what about quotients? What about functions that are quotients of other functions? Okay, so this is the quotient rule. All right, so we're going to say d of dx of some function which can be written as the ratio of two functions. I'm not going to prove all of this, obviously, but this is the general rule. It's very similar to the product rule, right? In the sense that you're just multiplying with the inverse of some other function, like 1 over g of x. So it looks kind of similar. So first you have the same thing as before, which is to say that g of x multiplied by f prime of x, okay? But now remember, when you were doing the product rule, you were adding the second part. Now, since you're dividing, in a way, that's why it's minus g prime of x multiplied by f of x. Okay, this is the quotient rule, and another important rule in calculus. Are there any questions so far? Okay. So let's do an example, and this function truly looks ugly, but using the quotient rule, we can get its derivative quite fast, actually. So let's look at this function, x cubed minus 3x squared minus 5 divided by 2x plus 5. Okay, and if we take the derivative of this function, respect to x. Okay, so let's apply the rule here. Okay, so first we take the numerator function, which is this one, and we differentiate, which is easy. It's x cubed, so that becomes 3x squared. Minus 3x squared becomes minus 6x, and minus 5, the derivative of minus 5 is 0, obviously. So that's the first thing. And then we multiply with the denominator, which is 2x plus 5. Okay. Then we subtract g prime of x. So that's the derivative of 2x plus 5, which is just 2. 2 multiplied by f of x, which is the numerator. So that's x cubed minus 3x squared minus 5. And then you divide it by the square of g of x, which is essentially 2x plus 5 all squared. Okay. And then this is pretty much it. I mean, you can distribute it as I've been doing before. And again, I'm not going to go over how exactly the algebra works out, but trust me, it does. And essentially what we are left with is 4x cubed plus 9x squared minus 30x plus 10 divided by 2x plus 5 squared. You can see that differentiation is quite mechanical, right? We know the rules. We know the rules for the power rule. We know the product rule. We know the quotient rule. We know the fact that constants can be taken out. We know the fact that you can distribute the derivative sign inside a function, inside sums of functions. And we just mechanically apply all of this, do some algebra, and we get the derivative, right, of almost every function. So far, we've only looked at polynomials because these are the nice functions and the algebra is easier. Let me give you the derivatives of some other elementary functions that cannot be expressed as polynomials, essentially. Okay. So first one is if f of x is the exponential function, so e raised to x or exp of x, then the derivative of that function is simply e raised to x. Okay. And if f of x is the log of x, then f prime of x is 1 over x. And then some trigonometric functions. If f of x is equal to the cosine of x or the cos of x, then f prime of x is in fact the sine of x. And then the last, useful one is if f of x is equal to sine of x, then f prime of x is equal to minus cos of x. Oh, sorry, it's the other way around, my bad. Apologies, it's minus sine and plus cos. Are there any questions? The questions have disappeared, so I'm just wondering if everybody is following. Okay. All right, no questions. The next and the last technique that we'll use before we think about second derivatives briefly is the chain rule. Okay. And essentially, the chain rule is finding derivatives using compositions of functions. Okay, so for example, if I had a function like so, and I wanted to find the derivative of this particular function, 3x cubed plus 2 raised to 100. Okay, now we could expand it out. That would be pretty annoying, right? I could not even write it. It would take you a long time to do it also. We could use the product rule, right? We could repeatedly use the product rule. But still, it's kind of hard to do with 100 in the exponent. But there is an easier way, which is to use the chain rule to compute derivatives of complex and weird-looking functions like this. Okay. So what we do is we do a substitution. Okay. We take this function and we break it into two functions, and we make this into a composition of those two functions. So what we say is let f of x be the thing inside the bracket here. So that's 3x cubed plus 2. Okay. And then we let g of x simply be x raised to 100. Okay. And these are nice functions because the derivative of both the f and g are relatively easy, right? And let me just write them down even, why not? So d of dx of f of x is 3 multiplied by 3, x raised to 2, so that's just 9x squared. And the derivative of g is 100x raised to 99. Okay, so these are easy. But the question is this thing, okay, so this function, this function is g of f of x. Okay, this is a composition. You can see that. We already discussed that in the beginning of the class. All right, so the question is, what is the derivative of this composition? Okay. And again, we can do this simply, right, by looking at two substitutions. Okay, we're going to call this thing y. Okay, and so we're going to say g, or we're going to say that y is equal to u of 100. Okay, and we're going to say that u is equal to 3x cubed plus 2. All right, and then we're going to use this equation, or we're going to use these identities with the chain rule, which is to say that dy of dx. So first you see that y is indirectly a function of x, right? It's actually a function of u, but indirectly it is a function of x, right? So dy dx, according to the chain rule, is simply the product of dy du multiplied by du dx, right? And essentially, I mean, this is abusing notation a little bit, but you can see the du in the denominator, du in the numerator, they can cancel out, right? So this is an identity of sorts. And in fact, this is the chain rule. This is in a box here. This is the chain rule, and it's super important. And using this, we can find the derivative of this composition here. Okay, and I don't have space here, so let me go into the next slide. All right, so I'm just going to rewrite dy by dx is equal to dy du multiplied by du dx. Okay, so this is the chain rule. All right, now our y was u raised to 100, and our u was 3x cubed plus 2. So if I want to find the derivative of dy dx, simply take the derivative of y with respect to u, and that's easy. That's 100 u raised to 99, okay, multiplied by du dx, which is kind of easy also. That's just 9x squared, okay? But we're not done yet because we want everything to be in terms of x, not u's. So we just replace the u here using this identity. So that's the same thing as 100 3x cubed plus 2 raised to 99 multiplied by 9x squared. And then in order to make things look nice, you just do 900 x squared 3x cubed plus 2 raised to 99. Okay, does this make sense to you guys? Chain rule? Okay, so let's do a function that has both, uses both the product rule and the chain rule. Okay, cool. Good to hear that you guys are following, at least some people are. It's hard on Zoom sometimes. Okay, so let's look at a function f of x. Okay, so now this is an even more complex function than we've done before, right? So that's 2x minus 3, so that's fine. But now we're multiplying it with x squared minus 5 cubed. Okay, so now we look at this function, we see it's a product, we say product rule. Cool, that's great. But then we see this thing here, right? We could do the product rule over and over again, but that would take too much time. But we can use the chain rule for this second product, which is raised to 3, right? So let's do the derivative. So let's do the derivative with respect to x of f of x. It's going to take a little bit longer. I'm going to do it step by step. So first we do the product rule, right? So that's saying take the derivative of the first thing, multiply it by the second thing, and then you add the first thing multiplied by the derivative of the second thing. Okay. Well, this thing is easy. It's linear in x, so that's quite nice. It's just 2. The derivative of this thing here is 2. So that's 2 times x squared minus 5 cubed. All right. And so far we are good. Now we have to derivate this thing on the right side, the last term. But we know that we can use the chain rule, right? We can just use the chain rule. So first we differentiate. We assume that x squared minus 5 is like some u. So we take the derivative of that u, of y with respect to that u, and that's just 3 times x squared minus 5, right? And then you multiply this with the derivative of the thing that's inside the parenthesis, which is 2x. Is everybody following how I did this? How I did this derivative here? If not, ask me a question, okay? And I'm having a look at the chat. But that's pretty much the same. That's pretty much the same thing that we did before. First, we took the derivative with respect to the whole thing, then we multiplied it with the derivative of the thing that's inside the parentheses or the brackets, okay? And then we just simplify things in order to make it look nice. So that's just 2 times x squared minus 5 cubed, okay? And then this is just 6x 2x minus 3 multiplied by x squared minus 5. Oh yes, squared. Thank you. See, thank you. You're correct. That was a mistake by my side. Thank you. All right, and then we can simplify this if you want. What we can do is we can just take x squared minus 5 squared common, and that just means that we have 2x squared minus 10 plus 12x squared minus 18x. And we can simplify this more if you want. Why not? Square minus 5 squared multiplied by 14x squared minus 18x minus 10. Okay, so we started with a function that looked kind of annoying, looked kind of complicated, but in fact it was not too bad using all the rules that we've learned. Let's do one more that is using a trigonometric function rather than polynomials. So suppose, please don't be on the board. Thank you. Okay, so now again, this is a composition of 2 functions. So we're going to use the chain rule, right? Okay, so first, the derivative of cos is minus sine. That's minus sine x raised to 4. Okay, and then we multiply it by the derivative of x raised to 4, which is 4x cubed. So that's just minus 4x cubed sine x raised to 4. Okay, looks pretty simple to do. And then the last one that we're going to do incorporates a lot of weird things, or more complex in a way. So that's just the square root of x cubed plus cos of x cubed. So now there are several compositions here. You have the square root here, you have something inside, and then you have cos with x cubed. So that's another composition. All right. But we can use the chain rule. We can just repeatedly apply the chain rule. Okay, so first we start with the big thing, which is the square root. So let's take the derivative with respect to x of this function, x. So first, this is equal to what? It's x cubed plus cos of x cubed raised to 1/2, because we know what square root is, it's just the power of 1/2. So first thing, we have the 1/2 out, okay? And then we have x cubed plus cos of x cubed is to minus half. Okay, then we go inside. Okay, so the derivative of x cubed is 3x squared. All right, and the derivative of cos of x cubed, now again we apply the chain rule here. So that's minus sine of x cubed, and then we differentiate x cubed with respect to x again. So that's 3x squared, right? And then we can simplify this. So that's so that's 3x squared minus, or let me just take that common. That's just 1 minus sine of x cubed divided by 2 times the square root of x cubed plus cos x cubed, and that's it, right? So all the rules that we've learned, if we apply them in conjunction with each other, we can differentiate pretty much any function or any smooth function that we can think of, which is why it's more mechanical than integration, which requires a little bit more thinking, but it's very powerful, right? Because we know exactly how a function, or a smooth function, at least a differentiable function, will be changing at any given point, right? And combining the information that we've done so far with first derivatives, which is to say that if we have a function f, right, and then f prime of x is the first derivative, and suppose if you wanted a function, or if you wanted to find what the maximum or the minimum of that function was, then this f prime of x is super important, right? Because let me give you an example. So suppose we have this function here. Okay, it's smooth. So suppose it goes something like this. Okay, and this function is defined from a to b, suppose. Okay, so in this interval, you can see that the slope is 0 for 2 points, right? One is what we'll call x lower bar here. Okay, and then the other is some point here, which we'll call x upper bar. So something like this. Okay, we know that the slope is 0, which means that that function has reached either the crest or the top, right? Minimum or the maximum. So that's great. If I have a smooth function, I know how to take the derivative of that function. If I set that derivative equal to 0, I will find a critical value, which is to say a candidate for either a maximum or a minimum. But because this is a smooth function, and in fact, suppose that it is twice differentiable. That is to say, suppose f prime of x is also differentiable. So that's also a smooth function. It's not always the case, by the way, but suppose it is differentiable. Okay. So now if you look at here, for all points that are slightly to the left of x bar, the slope will be positive, right? The slope will be positive. And then for all points that are to the right of x bar, the slope of that function will be negative, right? So that is to say the first derivative goes from 0 to negative, or after this point, okay? And here, if you look at it, as we move to the right of x lower bar, and for example, suppose we move to this point, we see that the slope is positive, the tangent of the tangent line to that function. Okay, so using this information, we can. I'm not going to prove this obviously, but this, assuming that this the first derivative is differentiable, gives us two very powerful results. Okay, the first is that if f prime at some point, so let's call it x star, and the second derivative, which is the derivative of the derivative at that point, is strictly negative, okay, that means x star is a local maximizer. Which is the case in this example with x bar, right? And so that's the first result. The second result is that if f prime of x star is 0 and the second derivative is positive, then x star is a local minimizer. Okay. So these are very powerful results. So using derivatives, and if the derivative is also differentiable using the second derivatives, we have conditions using which we know exactly where a function will be maximized or minimized on an interval. Okay. So these tools are quite powerful in that regard. All right. Let's do an example of that, and then we're going to take a break. All right. So let's just do one last example. So suppose we have a function f of x, which is 4x cubed minus 5x squared plus 2x. Okay. And suppose that this function is defined from 0, 1 interval to real line. Okay. So first thing, we take the first derivative. So f prime of x, this is a polynomial, it's super simple. So that's 12x squared minus 10 x plus 2. Okay. So what we do in order to find where this function reaches its maximum in this interval, we set this derivative equal to 0. And we call it a first order condition. And we write it FOC for short, or at least I do that. So that just stands for a first order condition. And so the first order condition simply says, set this derivative equal to 0 and then solve it. Okay. So if I solve it, I basically get, oh, sorry, up here. 10x plus 2. So now I can take the 2 common, I can put it on the right hand side. So that's just 6x squared minus 5x plus 1 is equal to 0. Okay, I continue solving this this equation, and I'm just doing algebra at this point, but you can obviously just use a computer to plug in, because it's a quadratic function, right? We're just finding the zeros of the quadratic function. So 6x squared minus 3x minus 2x plus 1 is equal to 0, which is the same thing as saying 3x common, 2x minus 1 times 2x minus 1 is equal to 0. Again, this is just algebra, so if you're a little confused or if I'm going too fast, just look over it again, all right, and have a look. After this example is done, then we take a break. So 2x minus 1 common multiplied by 3x minus 1 is equal to 0. Okay, so now we know what the roots are of this quadratic. All right, so basically we have 2 candidate solutions. I'm going to write that here, 2 solutions. First one is x1, which is equal to half, and x2, which is equal to 1/3. Okay, so we have 2 solutions, similarly to what we had like in this equation, in this example here, right? We had 2 places where the derivative was equal to 0. That is to say the slope was flat. There was no change you can make, or could not go lower or higher, but we don't know which one exactly, right? So we have two candidates here, and we want to see which one is a maximizer, which one is a minimizer. So what we do is we do the second order condition. We check the second order condition. Let me just write that. Second order condition. And that is to say, just take the derivative of the first derivative. So you do f double dash or f double prime of x. And that's basically taking the derivative of the first derivative. And that's 24x minus 10. And then you calculate this second derivative at this point and this point. Okay, so let's see. So if I do the second derivative at half, I get 12 minus 10, which is positive. Okay. And then if I take the second derivative at 1/3, then I get 8 minus 10, which is negative. Okay, so from all of this, I have concluded that in this interval 0 to 1, f reaches its max at, at x is equal to 1/3, and f reaches its min at x is equal to 1/2.
Подожди, а что-то неправильно по времени.
All right, let's take a 10-minute break. So it's 12:07 right now, so let's come back at 12:17, and we'll generalize whatever we've done into multiple dimensions. All right, so go ahead. Okay, let's start again so that we don't go over time. We already started a little bit late. So we had a question in chat said that in the last example, we said that X is the domain of X is between 0 and 1. And won't the minima and the maxima apply to the whole range, which I'm assuming we're talking about are. So let me, I was not completely precise here. So actually I was precise here, right? In the definition, I said a local maximizer, right? And a local minimizer. And that's saying that in some neighborhood around X bar, it's the maximum, okay? But for example, this function I said was, I was looking at it between the interval A and B, but perhaps it could go up forever, up before A and down forever after B, right? In which case the global maximizer would be some really negative number, right? Some really negative number. And the global minimizer would be some really high positive number, right? But we're looking at calculus. Calculus is the study of small variations. Now, so the results that we presented here are local results, right? They're saying that in some neighborhood around these 2 points, we know that X lower bar is the minimum and X upper bar is the maximum in that particular neighborhood, which was from A to B, right? In this picture. But globally, this may not be true, right? And you can go from global or local answers to global answers in certain conditions, like if this function was strictly concave, right? Or this function was strictly convex, then the local maximizer is in fact the global maximizer, but not necessarily the case. So that's why I wrote the local here, and which is again why in this example, I said, when I said max, I mean local max, right? And local min. And I'm looking at this particular neighborhood. And in fact, in this neighborhood, these are the maximizers and the minimizers, okay? And then one last thing that I want to talk about before I move on to multiple dimensions is this idea of a saddle point. All right, so I already drew it during the break, so we'll save some time here. So the idea is, let's look at this function here, okay? Fx cubed, okay? So the first derivative is f prime of x is 3x squared. And then the second, it's also, the first derivative is also differentiable. And in fact, it's 6x, the second derivative. So if you look at the first order conditions, we take the first derivative, okay? We set it equal to 0, which gives us the solution 0, okay? Then I look at the second order condition, I evaluate the second derivative at 0, and I find that it is also 0, okay? But if I look at the picture of x cubed, I see that at x is equal to 0, sure, the tangent line is, so the tangent line is 0, right? This is the tangent line, right? The slope of this thing is 0, but in fact, it's not a maximizer or minimizer. In fact, it is what is called a saddle point because of this shape here, right? You know what a saddle looks like. It's like some sort of basin, right? But it's not like a maximum or a minimum, all right? And so the point is that if the second derivative is equal to 0, that's not enough for us to conclude that at that point we have a maximum or a minimum, all right? It could be a saddle point. And these are slightly more technical concepts, but I thought this is interesting enough and important enough to mention. All right, so if there are no more questions, let's move on to the next part, which is multivariable calculus, unless there are any questions, and I'm happy to answer them. All right, we're fine. Okay, so now we're moving on to the next. And this is important because in machine learning, often you have algorithms that are choosing weights, right? And it's not just one weight, it's multiple weights. It could be like a large number of weights. So we need to be able to know how functions of multiple variables change as we change one or many of those variables, okay? And we're essentially building on what we have talked about so far in calculus of a single variable, okay? But we need a little bit more information in order to talk about in more detail how we can define derivatives in multiple dimensions, or when a function is a function of multiple dimensions. Okay, so first thing is, given some natural number n, okay, Rn, which is to say the real line, the Cartesian product of the real line, right, is the set of all lists of this form, which is x1, x2, x3, xn, where each of these numbers, right, xi, I'm writing I to just denote like a general number from this list, is a real number. And this is true for each I that is between 1 to n. Okay, so this is like we take a real line, and then, for example, R2 would be the two-dimensional plane, right? And two-dimensional and three-dimensional spaces are nice because they have like a geometric interpretation to it, and we sort of can imagine them in our head. So if n is equal to 2, right? Any point here, so for example, the point 1, 1 is both a point, okay? Another interpretation is that it's a vector, right? Which is to say it is the motion from the origin 0, 0. Right, so this is 0, 0. So you can think of it as a point, or you can think of it as a vector, which is to say motion from 0, 0 to someplace. Okay, and you can also do this in 3 dimensions. Obviously, it would be harder to draw. All right. So in general, if we have a point, and this interpretation, by the way, of a vector or of some point in some higher dimensional space, you can also extend that to any n, right? But it's just harder to imagine. It's nicer to draw in 2 dimensions and slightly more difficult in 3 dimensions. But suppose you have a point x that belongs to Rn. All right. What we do is, or what is usually the convention is, you write it as a column vector. So instead of like a list, you can also write it like so. Okay, this is, and you'll study more of this in the linear algebra course, which I don't remember exactly when it is. So I'm going to introduce to you concepts that are just about self-sufficient so that we can talk about differentiation and derivatives in multiple dimensions. Okay, but most of the linear algebra I leave to the other professor. So this is what is called a column vector. And it's a column vector because, well, I wrote it in a column, right? And then another thing, or a useful concept to know for us, is x prime, which is the transpose of x, and essentially takes a column and it makes it into a row vector. Okay, it's the row vector, and it's also the transpose. And you will learn more of this in the linear algebra course. So this is the transpose of x. Okay. And then the next thing that I want to introduce to you is something which is called the inner product or the dot product of 2 vectors. Okay. So given 2 vectors, x and y, that belong in this n-dimensional space, the inner product of x and y is basically given by this function here. So we say x dot y, okay? And that's equal to the transpose of x multiplied by y. And again, you will do this in linear algebra course, but I'm just going to show you very briefly. So the transpose of x is simply this row vector, as I said before. So that's x1, x2, all the way to xn. Okay, and then the y is a column vector. So that's just y1, y2, all the way down to yn. Okay, and then this is part of matrix multiplication. What you do is you multiply the first element of this row to the first element of this column. Then you add it to the product of the second element of this row and the second element of this column, and you add everything together. And it simplifies quite nicely. So that's just the sum from I is equal to 1 to n of xi multiplied by yi. Okay, and an interesting thing and an important thing to realize here is that these are vectors, right? This is an 1 by n vector. This is a 1 by n vector. This is an n by 1 vector. Okay, and then the dot product is in fact a scalar. It's a number, right? So this does not belong to Rn. It belongs to R. Okay, and this idea of a dot product allows us to generalize the notion of distances in multiple dimensions, because now we have n dimensions, right? Before we only had one real line, so the absolute value worked then. But now each point has n coordinates, where n could be greater than 2, or something really high. So we need some more technology, some more tools to discuss distances between points in Rn. All right, so let's see. So let x be a vector in Rn. Okay, so what we're going to define is what is called the Euclidean norm. Of x. Okay, and it's basically this function which uses the dot product. So we're going to call it with this norm sign. So it says the norm of x. And I do this dot. So first you see like the similarities between distance or like the absolute value function, but now I have 2 lines indicating that it's not one dimension, there are many dimensions. And essentially it is the square root of the dot product. Okay, so if I wrote this out, it would be the square root of the sum of squares of x. Okay, and there is a geometrical interpretation of this norm. Essentially, so for example, if I was in 2 dimensions, because it's easy to draw, as I said, if I was in 2 dimensions, okay, and I had some x, which was here. Right, so this is my x, this is the point x. Then this is the line from the origin to that point x. And essentially, the norm of x, which is the square root of x1 squared plus x2 squared, is just the length of this line, right? Does it make sense? You see how I did this? Basically, you can think of this as a right angle triangle here, right? Where this length is x2, this base is x1, and then this is just the hypotenuse, right? And the hypotenuse is equal to x1 squared plus x2 squared, and then this is just the distance. Okay? Does it make sense? So that's the idea of, well, that's what a norm is doing. Okay. So using this norm function, we can define the distance function in multiple dimensions. Okay, so in order to do that, we need 2 vectors. So let x and y be 2 vectors in Rn. Okay, and then essentially the distance the distance between x and y is given by the norm of x minus y. And that's pretty much equal to the square root of the sum of square differences. Okay, and this norm function and this distance function here has the similar properties and same properties, in fact, as the absolute value function, right? Because first thing is that since this is a positive number and this is a square root of a positive number, the distance between 2 points is always weakly positive. Okay, and the distance is 0 if and only if these are the same vectors. So that's pretty much the same thing as an absolute value function. Another property is that it doesn't matter if I take the distance from x minus y, it's the same as y minus x. And that's because I'm squaring here. And then the last is another version of the triangle inequality. That is to say that if I want to get from x to y, then the distance from x to y is weakly smaller than if I had gone through a third point. So for example, if I had gone to some z first, and then from z, I went to y. So that distance would have been slightly longer, weakly longer at least. Okay, so these are the same properties as the absolute value distance function in R1. Okay, so now what we're going to do is we're going to look at real valued functions of several variables. Okay, so this is going to be the focus of our next 40 minutes or so. All right, and in order to define a function, so we're going to say a function f that goes from Rn to R. Okay, that is to say, it takes a list of numbers, n numbers, and it maps it to some y in R. Right, so that's the f. Okay, so that's the idea, and that's the kind of functions we'll be looking at. In order to do that, we need to introduce some more ideas of what exactly does it mean to have like intervals in multiple dimensions. Okay, and we need some sort of order in Rn, because in R1 it's easy, it's greater than or equal to or less than or equal to, but it's a little more weird with multiple dimensions. Okay, so let's say, suppose we have two vectors in Rn. All right. We say that x is weakly greater than y if all coordinates of x are at least as big as the corresponding coordinate of y. Okay. X is greater than y if x is weakly greater than y and x is not equal to y. Okay, that is to say that there is at least one element of x which is strictly greater than that element of y. All right, and then the last thing is x is element-wise greater than y, and that is true if all elements of x are strictly greater than all elements or the corresponding elements of y. Okay, I'm going to write for each I again. And importantly, you can see that not all points can be compared, right? So for example, in 2 dimensions, because that's the easiest thing to look at, suppose we have a point, this point and this point, right? So we know that y is, in fact, y is element-wise greater than x in this case here. Okay. Now, if we look at a point, let's call it z here. Okay. So now z is greater than or equal to is strictly greater than x, right? Because on this axis here, it has the same value as x, but on this axis here, the y-axis, it has a greater value, right? And however, if we have a point here, then this is not really comparable with any of the orders that we've defined here, because on one dimension, so in the x-axis here, this point has a smaller coordinate than x, this point x, but on the y dimension, it has a higher coordinate or value than x. So we can't really compare this point, let's call it point B, with point x. We cannot use any of these operators here. Munas, I'm sorry, I don't understand your question, but we haven't really discussed, or this is not really going to be a linear algebra class. I'm not going to be discussing too much about the details of vectors and matrices. I'm just going to be introducing as much concepts as are necessary to talk about derivatives. Okay, so I'm going to not answer your question, but hopefully in the next linear algebra class, someone will answer your question. All right. Thank you. Okay, so let's move on. Now, as before, right, we want to talk about continuity, we want to talk about differentiability, but it's kind of annoying and kind of more confusing in these multiple dimensions, right? So first, suppose, please, Govind, can you erase that? Govind, you need to, thank you. All right, so given A and B, which are 2 points in Rn, such that every element of A is strictly lower than every element of B. Okay? We have intervals. So the first thing is AB, which is the closed interval, essentially is the set of all points in Rn that are weakly between X and B. Okay? And then the open interval, no worries, Govind, it's okay, is all points X that are element-wise greater than A and element-wise smaller than B. Okay, and if I draw it out, again in 2 dimensions, because that's the easiest thing to do. So if I have, let's say, an A here and a B here, essentially what we're doing is we're looking at the box that is defined like so. Okay. Pretty much, so it's not the best diagram, but that's the box that we're going to draw. Okay, and we're going to talk about continuity or sequences in this space here, right? So suppose I have a point here, which I will call x1, x2, right? So that's this point here, x1 and x2. First, what we're going to do is we're going to look at sequences that only look at the lines, that the vertical and the horizontal lines that are defined by x1 and x2. Okay, so basically we're only going to look at sequences that go like this, for example. That was not very well done, sorry about that. And from this side, like this. Okay, so we're only going to look at sequences like this. So what we're going to look at is what is called the coordinate-wise limit of points. Okay, so what we're going to do is we're going to take the point yi. So for example, we can take this point. Oh, I'm so sorry. This is. Okay, suppose we take like points from this point and then we just move them on one dimension, or we take these points and then we move them on this dimension towards x, right? So when I write yi to xi, I mean to say that I'm holding x1 fixed, for example, and then I'm choosing y2 and making it as close to x2 as possible. Okay, and I'm looking at the limit of the function that is defined over the space, right? So I'm going to look at the function, and what I'm going to do is I'm going to write this list in this manner, which is to say yi, which is the ith coordinate, and then I'm going to write x minus I, by which I mean all the other coordinates that are not I. Is this notation confusing If it is, then I can explain it in more detail. Because in this example, there were only 2 dimensions, right? But you could have n dimensions. So the way I do it is I isolate the ith dimension here, and then all the other dimensions, I put it in another list. Okay? And basically the idea is we're looking at one-dimensional limits. I'm only moving in one dimension, in one direction, which is either, in the 2-dimensional case, either vertically or horizontally. Okay? So we're going to treat all the other coordinates as fixed. Okay, so then we're going to look at limits like that, and we're going to say that the limit of f as x. So first of all, I want to point out one thing. Okay, so here we are only looking at one-dimensional limits, right? Like I'm only moving in either vertically or horizontally. But technically, we could be moving from any direction, and we could be choosing sequences that come in weird angles and weird ways all the way to that point, right? So this is one particular kind of limit, but in order for the limit to exist at that point, it must be true that for any direction that I approach this point in, the limit, all the limits that I calculate must be the same. Okay, so the limit of f as x approaches some point x naught exists if f of x n, well, the sequence, converges to some number L, right, which is a real number, for every sequence. And when I say sequence, I mean multiple dimensions. So like as I drew here, it would take like weird ways, right? Like this sequence goes like this sequence goes down, then up, and then back down. So for all of those sequences, if the limit is the same, then the limit exists and is given by Does it make sense, guys? It's the same idea as one dimension, right? In one dimension, we were only moving either vertically or horizontally. We were only taking like one side, one direction limits. But in multiple dimensions, we can approach that point x naught here, in multiple different ways, right? And the continuity and limits are defined if for any sequence that converges to that point, the limit exists and is the same, okay? And then continuity can be defined if f is continuous at x naught, if in fact this limit, which it exists, if it exists, is in fact equal to the function at that point. The sequence is so basically sequence is like a list, an infinite list of these xn's, right? Each of this xn is a list of length n. So the thing is, it's going to take us away from the true point of this class, which is to say that look at the differentiation of the derivatives. But in this example, you can see that, you know, if, for example, I draw like a parabola that passes through this point, right? Right? I can write x2 as a function of x1, or, you know, x2n as a function of x1n, for example. And that sequence, it will be a parabola, and it will converge to x1. Make sense? So that's the idea of continuity at a particular point. And then the same thing, f is continuous if it is continuous at every point, right? All right. So that's the idea of continuity. Basically, if I take any sequence in my Rn, so in this case, it's R2, that converges to a particular point, right? And if I look at if the limit of the function also exists for all of those sequences and is the same, and if in fact, if it is also equal to the actual function value at that point, then f is continuous at that point. And then f is continuous if it is continuous at every point in its domain. So it's the same idea as one dimension, all right? Okay, so now we're going to introduce what are called partial derivatives. They're using the same rules that we've developed before. But now, as you know, if I have a function that goes from some AB to R, now this AB is a subset of Rn. So there are multiple variables that I can choose, right? So what we do is we define what is called a partial derivative. So the partial derivative of f with respect to one of these variables, let's call it xi, right? It's the ith dimension. At that particular point or at a particular point that belongs in our domain. And it's the same idea that we've done in one dimension. It's basically given by, and now I don't write a d here, by the way, I write this cursive d. It just basically means partial, because now f is a function of multiple variables. So this is not the total derivative. This is only the derivative with respect to one variable. That's why I write this cursive d. Okay, so that's df dxi at this point x naught. And now it's pretty much saying that I take the limit, h goes to 0, and essentially the partial derivative is doing what we were doing in the beginning, right? We were only looking at either the horizontal or the vertical. So it's basically saying, take the ith dimension of x naught and then add h to it. Keep all the other coordinates minus I fixed. Okay. All right. Does this make sense to you guys? Let me draw this again. Okay. So basically, suppose I had a function of two variables. Suppose I had a function of two variables that was defined on some box like this. And I want to know what the derivative is at some point. So the partial derivative, so this is y, this is x. So the partial derivative with respect to y would be saying, take basically sequences that are going down like so, okay? And then let's look at the limit of the slope. The partial derivatives with respect to x would be saying, take sequence that arrive from the right here. So keeping y fixed, and then look at the slope, this slope, okay? So that's what a partial derivative does. So let's do a slightly more complex example, and I'm going to try and draw this in 3Ds to see if you guys understand what happens, okay? So suppose I have a function, f of x and y, all right? So I'm going to draw the xy plane here. This is y, this is x, okay? And it maps onto a a third dimension z. All right. And suppose it's like a sheet flying in the wind or whatever, right? So it's something like so. Okay, it's function like this. All right. And then I take a point here. If this is, let's say, x0, y0. Okay. And then I go on the surface here up top. Right. So suppose this is f of x0 and y0. All right. Maybe I guess in order to be completely accurate, it has to be slightly to the right here. Okay. All right. So now what partial derivatives are doing, they're saying, look at this line here. Which is parallel to the x-axis. Okay. And then you go up here and then you look at the slice of this sheet on this line. So it's going to look something like this. Okay. The partial derivative with respect to x essentially finds this slope. Okay. So this, the slope of this line, is the partial derivative with respect to x at x0. Okay. And then you can do the same thing with respect to y. So you basically take you draw a line that is parallel to the y-axis. Okay. And then you take the same thing there, right? And it's probably going to be something like so. All right. And then you look at the slope of that line, or the line that is tangent to that point here, to this curve. All right. And this thing, the slope of this line is the partial derivative. So slope of this line is the partial derivative of f with respect to y evaluated at this point. So remember that this is not the total derivative, right? It's only looking at two directions. Turns out these are super important directions to look at, right? But this function, we can move in this direction, right? We can move in this direction, we can move in this direction, we can move in this direction. And partial derivatives are not looking at all these directions. They're only looking at the direction which is parallel to the x-axis and the direction that is parallel to the y-axis. All right, but that is what they are doing. They're looking at those slopes. When I restrict my function to be on that line or this line, and then I draw a tangent line to that point. Okay, so that's what partial derivatives are doing. And then another an important thing and an important concept is called the gradient of f. If there are any engineers here, you've probably heard of this. So the gradient of f at x0 is, and it's denoted by this nabla function, or it's called nabla f x0, and that's essentially a list of all partial derivatives of f. So that's x1, x2, xn. Okay. So partial derivatives are essentially derivatives when I restrict my function to be on either the x or the y or however many dimensions I have, and then take basically the derivative of that particular slice of the function. And then if I collect them all together in a vector, that is called the gradient. Okay. And for optimization problems, including in machine learning, the gradient is very important. We're going to discuss why exactly the gradient is super important. And more importantly, now you know how to calculate it. It's super important because it's just partial derivatives, and they follow the same rules as all the derivative rules that we discussed in the first part of the class. So it's essentially the same thing over and over again, right? So it's not too bad. All right. But what is more important is why should we care about this in the first place, right? Why should we care about gradient? I told you it's important, but what exactly does that mean? And in order to understand that, we need to look at what is called a directional derivative. That is to say, what happens to a function if I choose in any direction, right? Because these derivatives are only looking at 1 or 2 or however many dimensions you have, specific directions. So we need to introduce the idea of a directional derivative. Okay. In order to do that, first, I think it would be important to think of the chain rule in multiple dimensions. All right. And let me tell you what sort of thing I'm looking for. All right. So suppose you have some variable y that you're interested in. Okay. And suppose it is a function of some x. But then x is just an intermediary variable. There is something else that affects x that affects y. Okay. Suppose it is t. Okay. And then I want to know how does y change as I change t? So the single dimensional chain rule, right, in the previous part of this course, we learned that this thing is in fact equal to, if I first look at how does y change as x changes, and then I multiply that with how does x change as t changes, right? That is simple. That is what we did before, okay? Now, suppose we had a slightly more complex function, right? So suppose we had like a w, that was our dependent variable, right? That is something that we cared about. And that two things affected w, x and y, okay? And there was a t that affected both x and y. So the question is, in this case, what would be the derivative of w with respect to t? Okay, and just going by the single dimensional chain rule, I'm not going to prove this, but we can show that w, our dependent variable, as a function of our independent variable, it changes like so. So first, we look at how it changes with respect to x, and then we multiply how x changes with respect to t. But that's not done, right? Because we covered this root here. We covered this root here. Okay, we know that w is affected by x, and we know that t affects x. So then the change from w, from the change in x, is given by this first equation here, this first product here. Okay, but that's not the whole thing, because we also have y here, right? So we have to add that effect. dt, okay? So now we're looking at how t affects either x and y, and how x affects w, and we add it together, right? And that's the multivariate chain rule, right? When you have a function that is a function of several variables, and then there is some other independent variable that affects both these things, and then we want to know the total change in w when I change my independent variable. And it's super simple. We just use the chain rule and we apply it several times and we add everything up. And that gives me the total effect of my independent variable, which is t in this case, on w, right? So let's look at an example, and then we'll go to the directional derivative, okay? So suppose w is equal to x squared minus y squared, okay? X squared is equal to t squared plus 1, and x is equal to 2, and y is equal to t cubed plus t. Okay, so we try to find the derivative of w with respect to t. It looks like a complicated problem, but we know exactly how x affects W, how Y affects W, and how T affects both of these things, right? So using the rule that we have okay, and then the partial derivative of W with respect to X, I'm just going to treat this as a constant, right? So that is to say it does not affect our function. Let's assume that. And that's just 2x, okay? And then the derivative of X with respect to T is 2t. And then the derivative of W, or partial derivative of W with respect to Y, is minus 2y. And then the derivative of Y with respect to T is simply 3t squared plus 1. Okay. Okay, so now suppose I said, okay, so this is like the total effect of T on W, depending on X and Y, right? Now suppose I asked you what is the effect of W, of T on W when T is equal to 0, all right? So first thing is, we don't really know what X is at T equal to 0, but we do, right? Because we have the function here. So that is equal to 2, and X is equal to, T is equal to 0, so X is 1, okay? And 2T is 0, so that's 2, 0, so that goes away. Minus 2Y, so Y is equal to 0, okay? Because when I plug in 0 here, Y is equal to 0, right? So that's 0. And then this is just 1. So it turns out that at T equal to 0, we have some sort of a critical point. It could be a maximum or a minimum with respect to T, right? Which is our independent variable. So this is the chain rule in multiple variables, and we can extend this in multiple different fashions, right? We could have, for example, we could have multiple independent variables. So you could have a case like, suppose you had a U and a V, and they both affected X and Y, and then X had a direct effect on W and Y had a direct effect on W. So this would be like this sort of a chain. And then if you want to know what is the effect of U on W, you would have to go through both X and Y, right? So then in this case, it would be like dW, du would be like the partial of W with respect to X, and now it's the partial of X because X is a function of two variables, partial of X with respect to U, W, Y, with respect to Y, partial of Y with respect to U, and then we can also have a total derivative of W with respect to V, and again, that's the same thing with V instead of U now. The point I'm trying to make is that single dimensional tools, or with respect to the chain rule, can be generalized in multiple dimensions in very nice and simple ways, right? Very understandable ways. Okay. And keeping all of this in mind, let's go to the directional derivatives. Okay. Because we are running out of time a little bit. Okay, so let's do the directional derivative. Now that we know what the chain rule is like, okay, and in order to just let me draw another function here. It's like some sort of a mountain, okay? Or a quarter of a mountain, let's just put it that way, okay? This is our surface, which is f of x and y. So this is x, this is y, all right? And we have some point here, which is x naught and y naught, okay? And this is the point on the surface. All right, and as we discussed, we have the y partial derivative, which basically looks at this curve here. Let's draw that here. Okay, and then that's the slope of this line here. Okay, and then we have we draw the line that is parallel to x here. And then that would be a function that looks like so. And then the slope, the partial derivative would give the slope of this tangent line here, right? But suppose instead of these directions, we wanted to move in some other direction, right? That is not either moving parallel to the x-axis or parallel to the y-axis. Okay. Suppose we wanted to move in, let's say, this direction. Okay. Essentially, this is a line, right? This is a line. Let's call it L, and it's moving in this direction. So this is the directional vector u. Okay, this is the direction of going in this way, right? And L basically can be written as so this is u. So L is basically all the points x0 plus u1t and y0 plus u2t, where u is u1 and u. It's basically a two-dimensional vector, right? Okay, and we want to know what happens if I look at, for example, the curve or the slice in this direction, which would be something like, probably something like so. Okay, I want to know what is the slope of this tangent line. All right. Well, it's actually kind of interesting because using the definition of a derivative, okay, the directional derivative, which is to say the derivative in a particular direction, not just x-axis or y-axis, the directional derivative of f at some point x0 in the domain that we're looking at, in the direction of u. And by the way, since it's a direction derivative, direction vector, the assumption is that the norm is 1. Okay, it's just pointing out the direction that I want to go in. The magnitude of that vector is 1. Okay, and this derivative is given by, and I'm going to denote it as du f of x naught. And that's the same thing as saying that I take the limit of points on this line and I approach this point x naught, 0 naught, right? And that's what I'm writing down here. I'm saying take this line, which is in the same direction as u, right? That's what I've written here. And take a sequence of points on that line only. All right. So then the directional derivative of f in the direction of u is given by this limit . Okay. It looks kind of weird, right? But in fact, it's really simple because of the chain rule, right? Because u is affecting x through u1, u2, u3, un. right? And then it's affecting the x's, correct? So essentially what we have is that du of f at a point is essentially the partial derivative of f with respect to x1 times the derivative of how that line changes with respect to u1, because that's like the x, right? That the points are on that line x. Plus, this is the chain rule, right? This is what we just did before. So I'm not going to like explain in detail, but that's the same thing. How does x2 change as I change u2? Or as I move down u2? Okay, and that's quite simple, right? We know what these are. These are the partial derivatives. And what is this? This is just u1, right? Or in fact, let me write it this way, because I define the line as some t, right? Right, because this line is defined as a function of t, right? So if I move things on that line, I have to change t, right? And by the chain rule, I know that this thing is equal to u1, this thing is equal to u2, this thing is equal to un, right? This is by the chain rule, correct? And if that is clear, if that makes sense, then essentially what we have is that the directional derivative in a direction u is simply the gradient, because this are all partial derivatives, which we long time back connected in a vector, which we call the gradient, and we take the dot product of this thing with respect to the vector u. Is everybody following me so far? Okay. So now the idea is the directional derivative of u is essentially just a dot product of the gradient multiplied by, or the dot product of the gradient and the direction that I want to go in, that I want to look at how this function will change if I go in that direction, right? And now let's just keep this in mind. But suppose you had two vectors u and v that were n-dimensional vectors. Okay, so recall the dot product of these two vectors is just u prime v, which is the sum of ui and vi products, right? But there is another way of writing this, which I'm not going to prove, but there is another way of writing it. It's basically the magnitude of u, or the norm of u, the norm of v, times the angle between these two vectors. Okay, so for example, if you have the vector u and the vector v, then this is the angle between them. Okay, and then there are some important properties here, in the sense that if this is a right angle, right? So if the angle between u and v is 90 degrees, right? Then this implies that cos theta is equal to 0. Okay, which means that the dot product of these two things is 0. Okay, and similarly, if these two vectors are going in the same direction, so this is u, and then the smaller vector is v, suppose. All right. In this case, cos theta is equal to 1. Okay, which means to say that u dot v is maximized if these vectors are moving in the same direction. And if these vectors are moving in opposite directions, so suppose u is moving in this direction and v is moving in this other direction. If that is the case, then then cos theta is equal to -1. So if they're moving in opposite directions, the dot product is minimized. Okay, so keeping this in mind, let's come back to the directional derivative, because it is in fact a dot product, right? So let me write this again. The directional derivative of function f in direction u at a point x0 is simply the dot product of the gradient, which is basically a vector of the partial derivatives of that function, and the direction u, okay? And we said, if you remember, u is just a direction derivative, so the magnitude of u is equal to 1, all right? So if we go by our other definition of the dot product, that's basically saying that this directional derivative is equal to the norm of my gradient multiplied by the norm of u, which by the way is equal to 1, so we're fine, multiplied by the cos of the angle between these two vectors, okay? So we're saying basically that if I choose the vector u such that it goes in the same direction as the gradient, so it's a directional derivative, that's why I have to divide it by the norm of the gradient. Okay, so this vector here, by the way, is moving in the same direction as the gradient. Okay, so I'm going to write that here in red maybe. Yeah, so this thing is to normalize, yes. Okay, so basically I'm choosing a vector that is a unit vector, so the norm is 1, but it moves in the same direction as the gradient. Okay, and if I do that, then according to what we just talked about here, because they're moving in the same direction, so cos is equal to 1, right? Which means that if this is true, if I choose this vector, then the directional derivative is maximized in that direction. That is to say, the directional derivative tells me in which direction to move to get the highest bang for my buck, right? So if I think of this mountain here that I drew here, basically the directional derivative will probably be something like in this direction, the gradient, okay? And then you look at, we look at this slice here, and then if I look at the slope, this is the highest that it can be, right? So the gradient will tell me in which direction to move so that I can get the highest ascent. And the negative of the gradient, which is to say minus, so that's in this direction, this will tell me which is the direction of the steepest descent. Is this clear? I'm sorry the picture wasn't very good. The pen isn't working extremely well today. Was that fine? Do you understand that? Okay, so this is the first result, that if I go in the same direction as the gradient, then I am going to have the steepest ascent. And if I go in the opposite direction of the gradient, so if u is minus, the same thing that I wrote before, so in the opposite direction as the gradient, then du is minimized. So this is why the gradients are super important, because they tell you, right? They tell you in which direction should you go if you want to maximize a function or if you want to minimize a function. So in machine learning, you have the gradient descent algorithm. And I think that's an algorithm that uses these tools and this idea that the gradient points to you in the way, in the place either where the function is going to be have the steepest increase or the steepest decrease. So in machine learning, if you have like a loss function and you're trying to minimize that loss function, the gradient will tell you in which direction you should go in to minimize that loss. Okay, so this is why gradients are super important. Does this make sense, guys? Let's do one example. And then we'll move to integration quite quickly. So suppose you have a function like this. Suppose you have a function like this. Okay, so it's a function of x and y. You want to know the derivative. So find, the exercise is to find the derivative of f of xy at the point 1, 2 in the direction u, which is given by this vector here. Okay, so very easy to do, right? I want to find the directional derivative. So what I need is the direction which is given, and I need to know the gradient. And the gradient is just the vector of the partial derivatives. So the gradient of f x is pretty much just the first derivative now let me just write xy. And then the partial derivative with respect to 1. Okay. So that is equal to, so this thing, first I differentiate with respect to x, and I keep y constant. If it's a constant, then it doesn't matter. So that's 3x squared minus 4x. Okay. And then the partial derivative with respect to y, again, x is constant, so all of this doesn't matter. And then the derivative with respect to y is just 3y squared. Okay. And then the next thing is, what is the directional derivative in the direction of u of f at the point 1, 2. Okay. So first of all, that is equal to, if I substitute 1 for x, then I get 3 minus 4, so that's minus 1. You know what, let me just, instead of x, y, write down the points here. So that's minus 1, and then y is equal to 2, so that's 3 times 4, so that's 12. Okay, and then you multiply that with u, which is, or the column vector u, which is root 3 by 2 and 1 by 2. Okay, and then simply do the matrix multiplication, which is to say that take this first element of this row, multiply it with the first element of this column, and then add it to the second element of this row and second element of this column, which is 6, and done, right? So basically in this direction, our function moves, or the slope of the line of the tangent at that on the surface at this point is this. Okay, so in fact, the function is increasing in that direction. All right, so that's the idea of a directional derivative. And in particular, we were talking about maxima, right? In particular, we have some nice results. So if x star is a local max, which is the same thing that we were doing in one dimensions, but now think of it in multiple dimensions, right? So if it's a local maximizer, of f, essentially what this means is that we've reached some sort of point where I cannot climb anymore, right? Going back to like that mountain thing that we had drawn here, essentially we're like somewhere here, right? We can't move any further. We've gone all the way to the top. The directional derivative is 0. Like it doesn't matter. I can't climb. So that basically means is that in no direction can I go, which will lead me to an increase. It will just leave me flat, right? So if x star is a local maximizer of f, then the directional derivative of f at x star has to be 0 for all u. Right? Doesn't matter what direction I go in. If it's a local maximizer, then I'm at top of some surface. At least locally, I can't do better. Right? And essentially, that's the same thing as saying that the directional derivative is 0. And remember, what is the directional derivative? Let's write it in some different color. So this thing is equal to the gradient x star times u. So this means that our gradient is 0. At that point. Okay. Does it make sense? So what we do is, if I want to find a point where I can't do any better or worse, right? If I want to find like a maximizer or a minimizer, it's like a simple procedure. All you do is you solve. So I want the gradient to be 0, right? So let me just write this more clearly. If you want to find a maximizer or minimizer, all you have to do is solve a system of n equations. And what are these equations? These are just the first order conditions with respect to the partial derivatives, right? Because the gradient contains all the partial derivatives. So if they are all equal to 0, that's the equation that you need to solve, right? You need to solve this equation here, which written down is essentially saying that df dx1 is equal to 0, df dx2 is equal to 0, and so on and so forth, right? This has to be true for all n variables, okay? And if we find like a point like that, then that's a candidate for a local maximizer or a minimizer. And in order to know if it's actually a maximizer or a minimizer, you need the second order conditions, which was the second derivative in the one-dimensional setting, right? In this two-dimensional setting, the second order conditions are a little more complicated because now second derivatives, it's not just a vector, it's a matrix. Okay, so I'm going to say in the multivariate setting, use what is called the Hessian. Okay, and that is defined as follows. It's a matrix, first of all. So let's call it H of f of x. Okay, essentially, it's a symmetric matrix where on the diagonal are the second partial derivatives. So that's d squared df dx1 squared d squared f dx2 squared all the way to d squared f dxn squared, okay? And on the off diagonals, it's basically cross partial derivatives. So for example, this one would be d squared f dx2 dx1, okay? And then go all the way down here to d squared f dxn dx1, okay? And basically it's the same here, so it's symmetric, right? This one is the same as this one is the same as this one, all right? Because of what is called Young's theorem, all right? It's a symmetric matrix, so let me just write that down here. So two variables I and j, xi and xj. It doesn't matter if I differentiate with respect to xi first or xj first, the cross partial is the same. Okay, this is what is the Young's theorem. So for example, on this side here, you would have d squared f dx1 dx2. So that's what I'm saying. This one is the same as this one. And this one will be the same as this one, and so on and so forth. So it's a symmetric matrix. Okay, so we're going to look at conditions in this matrix. Now, we don't have the linear algebra that we need to understand what that condition means. So basically, all I'm going to do is I'm going to write down the theorem or the statement, which tells you how what are the sufficient conditions for finding a local maximum in a function of multiple variables. And that condition or that statement is if the gradient at some point is 0, okay? And if the Hessian of that function at that particular point is negative definite, or in brackets, I'm going to write positive definite because basically negative definite is for a maximum and positive definite is for a minimum. Okay, so negative or positive definite. And hopefully in your linear algebra course, you will understand or you will learn what definiteness or semi-definiteness means. And if this is the case, then X star is a local max, or if it is a positive definite matrix, it's a min. Okay, so this is something that we will not show, primarily because we don't have the tools as of yet to understand what this definiteness is. But hopefully in your linear algebra courses, you will understand better what these conditions require, okay? But this is the idea behind derivatives and differentiation in multiple dimensions. And essentially the idea is that partial derivatives are super important because that in multiple dimensions will define a direction in which you can go in order to get the biggest increase or decrease in your objective function. So if you're an economist or a social scientist and you have like a game theoretic model, you have utility functions. So you will look for maximum, right? You will maximize utility functions. In machine learning context, you will have a loss function that you're trying to minimize. And for both these cases, you will be using optimization. And these are the basic tools of optimization that you would need, or you would at least need to know what they represent before you can learn exactly what those machine learning tools are, for example. Okay. All right, so in this last half an hour or so, I will just quickly discuss integration, okay? And I'm going to do this quite briefly because I don't have that much time left. We're going to do one example, and I'm going to state the fundamental theorem of calculus, okay? And we're only going to be working in one dimension because it's quite difficult to think of multiple dimension integrals. So essentially, the idea is, okay, so now we will talk about integrals. Okay, so the idea is, suppose you have a function. Okay, suppose you have a function that goes from A to B. Okay, suppose it's something like this, all right? and you want to know what is the area under this curve. Okay, that's what you're interested in. So the easiest way to do it, or to find this area, is what is called the rectangle method. Okay, so I'm going to write that down here. Rectangle method. So what you do is you divide this interval AB into bins, right? Equally spaced bins. And it's not completely equal, so let's just. All right. And then all you do is you draw like rectangles around your curve, right? So if you see what I've done, I've just taken the midpoint, I've gone down to the function, and then I've just made a rectangle here. So the idea being that these are not perfect representations or calculations of the area that is exactly under this curve, but it approximates quite well, right? And so the last one will probably be something like this. Okay, so this rectangles, if I add these rectangles up, this gives me a pretty nice. This gives me a pretty nice approximation of what this area is, right? And the idea is as I divide these partitions here, so let's just call it x1, x2, x3, so on and so forth, partitions more finely, that is to say, as I increase the number of partitions I have in this interval, okay, then my approximation will approach the true area. Under F, okay, between A and B on this interval. But we want to find a way to do this smoothly, right? Because this thing is not smooth. I'm dividing partitions in an interval. That's not super smooth. So we need a new mathematical tool by which we can say something about these areas here, okay? And essentially what we're going to do is we're going to define what is called an antiderivative. So basically we're undoing all the work that we did in the last 2.5 hours or so, okay? Basically you're saying, given a function f on some interval I, we say that capital F is an antiderivative of little f if the following condition is met. That is to say that for all x, if I differentiate my antiderivative, it will give me my original function back. Okay, so let's look at a simple example. All right, so suppose f of x is equal to x squared. Okay. All right, so what would be a candidate for f of x? If you're thinking about it, I want something that if I differentiate it, it gives me x squared. Okay, so a natural candidate is x cubed, right? Because then it becomes x squared. But that's not enough, because if I differentiate this, there's a 3 that comes out here, right? And someone has already written that here. It's basically x cubed divided by 3, right? If I take this function and I take the derivative of this function, then in fact it will give me my original function if I take the derivative of this thing. Okay, but let me ask you this, okay? What if I add a 7 here? All right, if I differentiate this function with respect to x, I would still get this, right? And the 7 is just completely arbitrary, right? What if I have like some random number, like square root of 2, any irrational number? It doesn't even matter, right? It doesn't matter, whatever number it could be, that the derivative of that function will still give me my original function. So that is to say that for each, so if I can find a family of antiderivatives for a given function, okay? So I'm going to write this as some constant c, it could be anything, okay? And this thing basically, or actually, let me write this in this manner. This thing, or this expression, basically represents the whole family of antiderivatives. Of little f. Okay. And this process of finding an antiderivative of a function is in fact what is integration. Okay. So it's not really connected to the area yet, as you can see, right? Because we haven't actually said much about the area. All we're saying is that if I can find an f a capital F such that if I take the derivative of that f with respect to x, then I get my original function back, okay? And then I can reverse this process, okay? And that idea is that if I integrate my original function with respect to x, then I get my antiderivative plus some constant, okay? So that's like the whole, it could be the, basically this integral has infinitely many solutions to it, okay? And this is what is called an indefinite integral. And it's essentially indefinite integral because I haven't actually given you any geometric interpretations of this yet. Okay, and when I talk about the definite integral, then there will be a geometric interpretation to this integral and there will be a definite area. But here we don't have an area yet, so it's an indefinite integral. Okay, and derivatives had a lot of rules, right? It was very nice. There was so many different rules. We could, do multiple things to a function and get really, simple derivatives, or at least get derivatives in a simple way. But integrals are a more complex beast. So what I'm going to do right now is I'm going to give you some common integrals. And the idea is that if you see an integral, so if you see a problem of this sort saying find the integral of this f, you try to manipulate f so that it looks as much as possible as the integrals that I'm just about to show you. Okay. So first thing is if I'm connecting it to the derivative, by the way, because essentially we're looking at antiderivatives, we're undoing derivatives, right? So suppose, or not suppose, but I know that the derivative of x is equal to 1, okay? Which means that the integral of a constant, or of 1, right, is in fact equal to x plus c, right? Because if I differentiate if I differentiate this is my antiderivative, I will get my original function. Oh, sorry, I will get the I will get my original derivative back, right? And then another one is d of dx of x raised to r, where r is any real number. I know that the derivative of this thing is equal to r times x raised to r minus 1, which suggests that the integral of x raised to r should be equal to, and we did that right here. We did that right here, by the way, and it's basically the whole generalization of that idea is that the integral should be the indefinite integral should be this, right? Because if I differentiate this, I will get this thing back. Okay. And another important one is to do with exponents. So for example, if I have an exponent, well, the derivative of the exponential is the exponential. If you remember, I did this, or I gave you this rule before, or gave you this identity before, which means that the integral of the exponential function is also just the exponential function, which is why it's a nice function. It's very well behaved in that sense. Okay, and then assuming that x is positive, then we know that the derivative of the log of x is 1 of x, which means that I can convert this into an integral, right? Because if I integrate 1 over x, it will give me the log of x plus c, because if I differentiate this log of x, I will get 1 of x, right? So I'm just using the idea of an antiderivative here. And then the last thing I'm going to do is sine of x and cos of x. So I know that the derivative of sine of x is cos of x, which means that if I integrate cos of x, then I should get sine of x. So see, this is my antiderivative, right? Because if I differentiate this, I will get f, little f. And then the last one is, I know that the derivative of minus cos of x is sine of x, which means that if I integrate sine of x, I should get minus cos of x. Right? So this is the connection between what is a derivative and what is its antiderivative. Just using the idea that the antiderivative is essentially a function, so that if I differentiate that function, it will give me my original function. Okay. So there are some basic rules and tricks. So let me just give you these basic rules and tricks, and then I'm going to just state the fundamental theorem of calculus and then the idea of what this integral does. You will not be using this, well, you will be using these ideas more in your probability and statistics course, which will also come after this one. So I'm not going to go into great detail, and we're pretty much out of time already. So what we're going to do is we're going to do some basic rules of integrals. Okay, so the first thing is that differentiation is linear, right? That is to say, dx of f of x plus g of x is equal to d of dx of f of x plus d of dx of g of x. Okay, we know this, right? But this actually implies that so is integration, right? Because if you let f prime is equal to f, okay, and g prime is equal to g, all right? If this is true, then if I take c, which is some constant, let's say c1 of f plus c2 of g, capital G, and I take the derivative of this thing, if this is true, if these two things are true, then this in fact will give me c1 times little f plus C2 times little g. Okay, which then implies that if I integrate C1 F1 of x, or not F1, just F of x plus C2 g of x with respect to x, then I can take the constants out, okay, and then I can just distribute the integral sign inside, right? So then this is just f of x with respect to x plus C2 times the indefinite integral of g of x with respect to x. Okay, so that's the first rule. That's because differentiation is linear, so is integration. So are integrals or antiderivatives. Okay. The second thing says that product rule gives us integration by parts. Okay. So basically, the idea is, suppose you have a function that is the product of two functions. We have x, f of x, and g of x. Okay, and then if I take the derivative, this is the product rule, right? What do I get? I get that f prime x times g of x plus g prime of x times f of x. This is just the product rule. We've done this before, right? So now, if I integrate both sides, I get it's just the opposite, right? The differentiation and integrals are basically inverses in a way. And then if I arrange things, then I basically get that if I have a function that looks something like this, that is basically, it looks like a product of a function and the first derivative of some other function, then I can rewrite this like this. So sometimes, for example, it is more easy to calculate f prime than it is to calculate g prime, or the integral of f prime times g instead of f times g prime. So basically, if this integral is very difficult to do, but if this integral is easy, and I will give you an example in just a second, then you can use this product rule trick and do integration by parts. Basically, you divide this integral up into the product plus or minus this other integral, which is easier to compute, right? And then the last thing, and then I'm going to give you an example, and then just briefly state the fundamental theorem of calculus. And basically, these concepts, you will use them in the probability and statistics courses. So the last one is the chain rule. So that's the third basic rule. So chain rule gives integration by substitution. Okay, and that's the idea. That's pretty much the same idea that we've been using with the chain rules. If you have an integral of a composition, okay, if you have an integral of a composition that looks something like this, okay, we can rewrite this as the integral of just this function g u with respect to u, right? So basically, I make f of x u. So what I do is I let u is equal to f of x, okay, which means that du dx is equal to f prime of x, okay, which basically means that dx is equal to du is equal to, which means that du is equal to f prime x dx. So basically, I can use these identities here and I can substitute them here. And I get this new integral, which is sometimes easier to compute than this composition type integral. Okay. And I'm going to give you an example or a couple of examples of this integration by parts and this integration by substitution. So the first example is what is the integral of log of x dx? Okay. And what we do is we do this by parts, all right? Because if we let g of x to be log of x and f of x as x, okay, so it's really easy for me to compute the derivative of this, right? And when I multiply it, the derivative of this with this, that becomes 1, right? So let me write that here. So f prime of x means it's just 1, okay? And g prime of x is equal to 1 over x, okay? And then what I'm going to do is I'm going to use the substitute rule, and I'm going to say that this thing is equal to g times f, so that is x times log of x, okay, minus the integral of g prime, which is 1 over x, right? So think about it. This thing is essentially g of x multiplied by f prime of x, right? So that's what I'm using. I'm using integration by parts by recognizing that this function can be written like this, and then using by parts because g prime is 1 over x and f is x, right? So this just cancels out. This just becomes 1, and I know how to take the integral of a constant, right? So this thing is just x plus c, log plus c, log of x minus x plus c, right? So it looked complicated. I didn't really know how to manipulate this, but if I use this trick or this integration by parts idea, then I get a closed form solution or closed form expression of this integral. Okay, and then I'm going to do one last example, and then I'm going to state the fundamental theorem of calculus, and I'm going to stop there. Okay, and the same idea here. So if I'm finding the integral of r to the x, this is kind of weird. We know how to do x to the r, but we don't really know how to do r to the x. Okay. All right, so what we do is we do it by substitution. All right, and this is kind of weird, but we're going to use log and exponents and the fact that they are inverses of each other. Okay, so what we're going to do is we're going to let u is equal to log of rx. Okay, and if I take the log, I can take the x out. It's the same thing as saying it's x log r. Okay, so now separated x and r, which is good because r raised to x is kind of weird because I'm looking at the integral with respect to x, not r. All right, and also, by the way, r is greater than 0. All right, and then this implies that du dx is simply log of r. Okay, using this idea, we're going to look at the integral that we started out with, okay? And then we're going to use our u's with the logs and the exponents to write it in this manner, okay? So I'm going to say that this is the integral of the exponential of log r times x, okay? So basically this thing is this thing, and if I take the exponent of this thing, I'll just get this thing. Right, so this is fine. I can do that. Okay, dx. Okay, and then what I'm going to do now is I'm going to use the fact that du is equal to log r times dx. Okay. So what I'm going to do is I'm going to take the exponential of u, because this thing is u. Okay. Then I'm going to divide it by log of r, right? Because dx if I go down here, I can say that dx is equal to du divided by log of r, right? So I'm basically substituting for dx here, which means I get this. Okay, now I know the integral with respect to the exponential function, because now the integral is with respect to u, right? And that is simply the exponential of u divided by log r plus a constant, okay? And then exponential of u is nothing but r of x, right? So that's just r of x divided by log r plus the constant, all right? So this is how we use integration by substitutes to solve complex integrals or more complex integrals, because integration is less rule defined than is differentiation. So you need to do a little bit of tricks and trickery here and there, okay? And all I'm going to do now, I'm just going to write down the fundamental theorem of calculus just to tell you where exactly we use these antiderivatives. And essentially the fundamental theorem of calculus establishes the relationship between integrals and the antiderivatives, or definite integrals and the antiderivatives. Okay, it says that if f is a function from some interval ab to r, and it is continuous, and has an antiderivative, capital F, okay, then the definite integral, so from a to b, the definite integral of my function with respect to x is simply fb minus fa, which is why the constants cancel out. So that's why I didn't really go into much detail, but if you remember, in the indefinite integrals, we had these constants, but if you're evaluating a definite integral, then these constants will cancel out, right? Because it'll be plus c minus c, it will cancel out, okay? So what antiderivative we used exactly is immaterial, right? Because that constant will just cancel out. And then the second thing, which I will not prove, is that this thing here, which is the definite integral, we know exactly how to calculate it. This, in fact, is the limit of that rectangle method that we began with, okay? So basically, it's the limit of the sum of the area of those rectangles. So for example, if I had divided my interval up into n partitions, okay, and if I basically keep on taking n to the infinity, right, I make them smaller and smaller partitions, this thing will in fact converge to this thing, which is to say that the definite integral is in fact, so let me write that down here and then we are done. So that this implies if this is the limit of this rectangle sum, or the area of all those rectangles that we discussed just a few slides back, then in fact this definite integral is the area under the graph of f over the interval a, b, okay? So that's it. I'm not going to prove this obviously, but this is what you will use when you talk about continuous probability distributions. All right, it was a very dense morning and afternoon for you, for me and for you. So thank you so much for paying attention, and good luck with the rest of your program. Yeah, good luck with everything. Take care.